All right, looks like I'm now live. Unfortunately, this is something that's been a little bit annoying because it takes me about 15 minutes to figure this out. So I don't promise I'm going to be prompt every day because this streaming software seems to be kind of buggy and it's only allowing me to go live some of the time and I'm logging in and out. All right, enough of that. Let me just update that I'm now live on the website. Let's just make sure that's working. We just added a new banner feature showing the project. Oh my God. Hold on a sec. Oh, weird. Don't know why that's not working. All right, new things to do with live streaming requiring me to figure stuff out. We will just try to have, okay. All right, I will just put this away for right now. And let's get back to learning quantum mechanics. So just to briefly catch you in if you're just coming in. So I've gone through some of the problem sets. I'm going through the lectures right now. My goal is to get to lecture 10 so I can get through problem sets 1 to 5. I'm on lecture 6 right now. We started watching it in the morning. I ended off kind of about 20 minutes into that one. I'm going to finish lecture 6. I'm going to try to get as far as I can in this afternoon, finishing the lectures, just trying to understand them at a high level. I know there's probably going to be work to be done to like really get it at the mathematical level, especially when we're solving problem sets. But I figure getting through the first 10 is going to be how we can start doing these problem sets, good chunk of the class. So I'm going to shift over and start doing it. And as always, if you're having difficulty understanding anything that's happening in the lecture, you can go get it at MIT's OpenCourseWare. Just look for the spring 2013 session of 8.04 Quantum Physics 1. And that's the one I'm doing the lectures with Alan Adams. This is lecture number 6.
So you throw stuff in, you form a black hole, you have a horizon, if you fall through that horizon, and you never see you again. Surprisingly, a black hole is a hot object like an iron, and it sends off radiation. Okay? As it sends off radiation, it's losing its energy, it's shrinking. And eventually, it will, like a classical atom, collapse to nothing.
So when you start listening to someone really fast, it seems super fast, and then you get used to it faster and faster. So I usually slow them down when I start listening to it to get my ear picked up to it.
So, but here's the funny thing. If you threw... and then the black hole evaporates, where did the information about what made the black hole go if it's just thermal radiation coming out? So this is a classic calculation which to a theorist says, aha, maybe unitarity is concerned. But look, black holes, theorists, there's no experimental violation of unitarity anywhere. And if anyone ever did find such a violation, it would shatter the basic tenets of quantum mechanics, in particular the Schrödinger equation. So that's something we would love to see but never have. Depends on your point of view, you might hate to see it. And the third, and this is, I think, the most important, is that the Schrödinger evolution, this is a time derivative. It's a differential equation. If you know the initial condition and you know the derivative, you can integrate it forward in time. And there exists some unique theorems for this. The system is deterministic. What that means is that if I have complete knowledge of the system at some moment in time, if I know the wave function at some moment in time, I can determine unambiguously the wave function at all subsequent moments of time. Unambiguously. There's no probability, there's no likelihood. It's determined, completely determined. Given full knowledge now, I will have full knowledge later. Does everyone agree that this equation is a deterministic equation in that sense? Question. Well, okay, this one happens to be, you need to give me a better definition of local. So give me a definition of local that you want. No, unfortunately, it's not the case. We'll see counterexamples of that. The wave function, the energy operator, let's see what this equation says. What this says is the time rate of change of the value of the wave function some position at some moment in time is the energy operator acting on sine x of t. But I didn't tell you what the energy operator is. The energy operator just has to be linear. It doesn't have to be, you can know about the wave function everywhere. The energy operator is a map that takes the wave function and tells you what it should be later. And so at this level, there's nothing about locality built into the energy operator. And we'll see just how bad that can be. So this is related to your question about special relativity. And so those are deeply intertwined. But we don't have that property here yet. But keep that in your mind and ask questions when it seems to come up. Because it's a very, very, very important question when we talk about relativity. Yeah.
For postulate 6 and 3, that if the Schrödinger equation has superposition in it?
No, excellent question. So postulate, that's a very good question. The question is, look, there's postulate 3, which says given any two wave functions that are viable wave functions of the system, then there's another state which is a viable wave function at some moment in time, which is also a viable wave function. Okay, but the number 6, the Schrödinger equation, or sorry, really the linearity property of the Schrödinger equation is so it needs to be the case for the Schrödinger equation, but it does something slightly different. It doesn't just say that any plausible or viable solution of the any plausible or viable wave function and another can be superposed. It says that specifically any solution of the Schrödinger equation plus any other solution of the Schrödinger equation is again a solution of the Schrödinger equation. So it's a slightly more specific thing than postulate 3. However, your question is excellent because could it have been that the Schrödinger evolution didn't respect superposition? Well, yeah, you could imagine such. Sure, we could have done a different equation. Right? It might not have been linear. We could have had that Schrödinger equation was equal to dt sine. So imagine this equation. How could we have blown linearity while preserving determinism? So we could have added plus, I don't know, psi squared of x. Right? So that would now be a nonlinear equation. It's actually referred to as the nonlinear Schrödinger equation. Right? Well, people need to think about the nonlinear Schrödinger equation. That's a nonlinear Schrödinger equation. So you can certainly write this down. It's not linear. Does it violate the statement 3 that any two states of the system could be superposed to give another viable state at a moment in time? No, right? It doesn't directly violate it. It has a spirit of it, right? And that's something I actually would call this dramatic problems. It's something we don't usually emphasize. This is something we don't usually emphasize much in before, but I will make a specific effort to mark the places where this would cause disasters. Okay? But so this is actually a logically independent, although morally, and in some sense, technically related point to the superposition principle number 3. Yeah.
For postulate 3,
yeah.
Can I have some the system?
Absolutely.
That makes them like creating discontinuous wave functions.
Oh yes, you can. So here's the thing. Look, if you have two functions and you add them together, like two smooth continuous functions, you add them together, what do you get? You get another smooth continuous function, right? Take 7. You get another, But if you take an infinite number, look, mathematicians are sneaky. There's a reason we keep them down that hall, right, far away from them. So they're very sneaky. And if you give them an infinite number of continuous functions, they'll build for you a discontinuous function, right? Sneaky. Does that seem terribly physical? No, it's what happens when you give a mathematician too much paper and time, right? So in any physical, so here I mean this less literally than I'm saying it, but yeah, it's worth being a little flippant here. In a physical setting, we will often find that there are effectively an infinite number of possible things that could happen. So for example, in this room, where is this piece of chocolate? It's described by continuous variable. That's an uncountable infinite number of positions. Now in practice, you can't really build an experiment that does that, but it is in principle an uncountable infinity of possible positions, right? You will never get a discontinuous wave function for this guy, because it corresponds to divergent amounts of momentum, as you showed in the previous problem set. Okay. So in general, we will often be in a situation as physicists where there's the possibility of using the machinery, the mathematical machinery, to create pathological examples. And yes, that is a risk, but physically never happens. Physically, it's extraordinarily rare that such infinite divergences could matter. Now, I'm not saying that they never do, but we're going to be very carefree and casual in before, just assume that when problems can arise from, say, superposing an infinite number of smooth functions leading potentially to discontinuities or singularities, that they will either not happen for us, not be relevant, or they will happen because they're forced to. So for physical reasons, we'll be able to identify. So this is a very important point. We're not proving mathematical theorems. We're not trying to be rigorous. To prove a mathematical theorem, you have to look at all the exceptional cases and say, those exceptional cases, we can deal with them mathematically. To a physicist, exceptional cases are exceptional. They're irrelevant. They don't happen. It doesn't matter. Okay? So, and it doesn't mean that we don't care about the mathematical precision, right? I mean, I publish papers in math, sure. So I have a deep love for these questions, but they're not salient for most of the physical questions we care about. So do your best to try not to let those special cases get in the way of your understanding of the general case. I don't want you to not think about them. I just want you to not let them stop you. Okay? Yeah.
But you have the constant effect as a experiment that more or less proves this class of the waveform. So I grab that is not conclusive.
Yeah.
Is that an experiment that is?
Yeah. So as with different questions. So let me make a slightly more general statement than answering that question directly. Many things will how to say. So we will not prove. And experimentally, you almost never prove a positive thing. You can show that a prediction is violated by experiment. So there's always going to be some uncertainty in your measurements. There's always going to be some uncertainty in your arguments. However, in the absence of a compelling alternate theoretical description, you cling on to what you got as long as it fits your data. And this fits the data like a champ, right? So does it prove? No, it fits pretty well, and nothing else comes even within the ballpark. And there's no explicit violation that's better than our experimental uncertainties. So I don't know if I'd say we could prove such a thing, but it's it fits. And I'm a physicist. I'm looking for things that fit. Right? I'm not a metaphysicist. I'm not trying to do some ontological commitment about what things are true and exist in worlds, right? That's not my job. Okay, so much for our review. So let me finally come back to, now that we've observed this determinants, let me come back to the question that was asked a few minutes ago, which is, look, if we take this equation, and suppose we take our superposition state, we evolve it forward for some time using the Schrödinger evolution. Notice that it's time reversal. If we know it's time reversal, we can run it backwards just as well as we could run it forward, right? We can integrate that time back, we can integrate that time forward. So if we know the wave function at some point in time, we can integrate it forward, we can integrate it back in time. But if at some point we measure, then the wave function collapses. And subsequently, the system evolves according to the Schrödinger equation with this new initial condition. So now we seem to have a problem. We seem to have, and I believe this is the question that was asked. I don't remember who asked it. Who asked it? Okay, so someone asked, it was a good question. We have this problem that there seem to be two definitions of time evolution in quantum mechanics. One is a Schrödinger equation, which says that things deterministically evolve forward in time. And the second is collapse, that if you do a measurement, things non-deterministically, by probabilities, collapse to some possible state. Yeah? And the probability is determined by which wave function you had. How can these things both be true? How can you have two different definitions of time evolution? So this sort of frustration lies at the heart of much of the sort of spiel about the interpretation of quantum mechanics. On the one hand, we want to say, well, the world is inescapably probabilistic. Measurement comes with probabilistic outcomes and leads to collapse of the wave function. On the other hand, when you're not looking, the system evolves deterministically. And this sounds horrible. It sounds horrible to a classical physicist. It sounds horrible to me. It just sounds awful. It sounds arbitrary. Meanwhile, it makes it sound like the world cares. It evolves differently depending on whether you're looking or not. And that, come on. I mean, I think we can all agree that that's just crazy, right? So what's going on? So for a long time, physicists in practice, and still in practice, but for a long time, physicists almost exclusively looked at this problem and said, look, don't worry about it. It fits the data. It makes good predictions. Work with me, right? And it's really hard to argue against that attitude. You have set of rules. It allows you to compute things. You compute them. They fit the data. Done. That is triumph. But it's deeply disconcerting. So over the last, I don't know, in the last quarter, roughly, the last third of the 20th century, various people started getting more upset about this. So this notion of the, just shut up and calculate, which has been enshrined in the physics literature, goes under the name of the Copenhagen interpretation, which roughly says, look, just do this, don't ask, compute the numbers, and get what you will. And people have questioned the sanity or wisdom of doing that. I think there's an idea. So I refer to the Copenhagen interpretation with my students as the cop-out, because it's basically a disavowal of responsibility. Look, it doesn't make sense, but I'm not responsible for making sense. I'm just responsible for making predictions. Come on. So more recently, I've found the theory of decoherence. And we're not going to talk about it in any detail until the last couple of lectures of the day before. Decoherence. I can't spell this in life. So the theory of decoherence, and here's roughly what the theory says. The theory says, look, the reason you have this problem between, on the one hand, Schrödinger evolution of a quantum system, and on the other hand, measurement leading to collapse, is that in the case of measurement leading to collapse, you're not really studying the evolution of a quantum system. You're studying the evolution of a quantum system, i.e. a little thing that you're measuring, interacting with your experimental apparatus, which is made up of 10 to the 27 particles, and you made up of 10 to the 28 particle, whatever. It's a large number, a lot more than that, but you, right, a macroscopic object, where classical effects or classical dynamics are a good description. In particular, what that means is that the quantum effects are being washed out. You're washing out the interference fringes, which is why I can catch this and not have it split into many different possible wave functions of where it went. So dealing with that is hard, because now if you really want to treat the system with Schrödinger evolution, you have to study the trajectory and the motion and the dynamics of every particle in the system, every degree of freedom in the system. So here's the question that decoherence is trying to ask. If you take a system where you have one little quantum subsystem you're trying to measure, and then a gajillion other degrees of freedom, some of which you care about, they're made of you, some of which you don't, the particles of gas in the room, the environment. If you take that whole system, does Schrödinger evolution, in the end, boil down to collapse for that single quantum microsystem? And the answer is yes. Showing that takes some work. And we'll touch on it at the end of the E4. But I want to mark right here that this is one of the most deeply unsatisfying points in the basic story of quantum mechanics, and that it's deeply unsatisfying because of the way that we're presented. And there's a much more satisfying, although still, you never escape the fact that quantum mechanics violates your intuition. That's inescapable. But at least it's not illogical. It doesn't directly contradict itself. So that story is the story of decoherence. And if we're very lucky, I think we'll try to get one of my friends who's a quantum computing guy to talk to us. Yeah. No. There's never any ambiguity about what result you got. You never end up in a state of, this is also something that decoherence is supposed to explain. You never end up in a situation where you go like, wait, I don't know. Maybe it was here, maybe it was there. I'm really confused. I mean, you can end up in that situation because you did a bad job, but you don't end up in that situation because you're in a superposition state. You always end up, when you're a classical beast, you make a classical measurement, you always end up in some definite state. Now, what wave function describes you doesn't necessarily correspond to you being in a simple state. You might be in a superposition of thinking this and thinking that. But when you think this, that's in fact what happened. And when you think that, that's in fact what happened. Okay, so I'm gonna leave this alone for the moment, but I just wanted to mark that. It's an important part of the quantum mechanical story. Okay, so let's go on to solving the Schrödinger equation. So what I want to do for the rest of today is talk about solving the Schrödinger equation. Okay, so when we say about solving the Schrödinger equation, the first thing we should realize is that at the end of the day, the Schrödinger equation is just some differential equation. And in fact, it's a particularly easy differential equation. It's a first-order linear differential equation, right? We know how to solve those. But while it's first order in time, we have to think about what this energy operator is. So just like the Newton equation, F equals ma, we have to specify the energy operator before we can actually solve the dynamics of the system. In F equals ma, we have to tell you what the force is before we can solve for P, from P dot is equal to F. So for example, one strategy to solve the Schrödinger equation is to say, look, it's just a differential equation. And I'll solve it using differential equation techniques. So let me specify, for example, the energy operator. What's an easy energy operator? Well, imagine you had a harmonic oscillator, which, physicists, that's your go-to. So harmonic oscillator has energy p squared over 2m plus m omega squared upon 2 x squared. But we're doing quantum mechanics, so we replace these guys by operators. So that's an energy operator. It's a perfectly viable operator. And what is the differential equation that this leads to? What does the Schrödinger equation leads to? Well, we got to put the IH bar on the other side. IH bar, derivative with respect to time, psi of x and t, is equal to p squared. Well, we remember that p is equal to h bar upon I, derivative with respect to x. So p squared is minus h bar squared, derivative with respect to x squared.
All right. Let's go a little slower here. I'm going to be missing some of this math if I go too fast. This is
Or minus h bar squared upon 2m psi prime prime, or let me write this as dx squared, two spatial derivatives of acting on psi of x and t, plus m omega squared upon 2 x squared psi of x and t. So here's a differential equation. And if we want to know how does the system evolve in time, i.e. given some initial wave function, how does it evolve in time, we just take this differential equation and we solve it. And there are many tools to solve this partial differential equation. For example, you could put it on Mathematica and just use ND-solve, right? This wasn't available, of course, to the physicists at the turn of the century, but they were less timid about differential equations than we are because they didn't have Mathematica. So this is a very straightforward differential equation to solve, and we're going to solve it in a couple of lectures when we're studying the harmonic oscillator in detail. What I want to emphasize for you is that any system has some specified energy operator, just like any classical system has some definite force operation or force function. And given that energy operator, that's going to lead to a differential equation. So one way to solve the differential equation is just to go ahead and brute force solve it. But at the end of the day, solving the Schrödinger equation is always going to boil down to some version, morally, of solve this differential equation. Questions about that? Okay. But there are actually, when we actually look at a differential equation like this, so say we have this differential equation, it's got a derivative with respect to time, so we have to specify some initial condition. There are many ways to solve it. So given E, so given some specific E, given some specific energy operator, there are many ways to solve the resulting differential equation. And I'm just going to mark that in general it's a PDE, because it's got derivative with respect to time and derivative with respect to space. Okay. And roughly speaking, all these techniques fall into three camps. The first is just brute force. Okay. That means some analog of throw it on Mathematica, go to the closet and pull out your mathematician and tie them to the chalkboard until they're done and then put them back. But some version of brute force, which is just use by hook or by crook some technique that allows you to solve the differential equation. Okay. The second is extreme cleverness. Okay, and you'd be amazed how often this comes in handy. So extreme cleverness, which we'll see both of these techniques used for the harmonic oscillator. That's what we'll do next. Force, and secondly, the clever way of solving the harmonic oscillator. When I say extreme cleverness, what I really mean is a more elegant use of your mathematician. You know something about the structure, the mathematical structure of your differential equation. Okay, and you're going to use that structure to figure out the good way to organize the differential equation, the good way to organize the problem. And that will teach you physics. And the reason I distinguish brute force from cleverness in this sense is that brute force, you just get a list of numbers. Cleverness, you learn something about the way the physics of the system operates. We'll see this at work in the next two lectures. And see, I really should separate this out numerically. And this, and here I don't just mean sticking it into MATLAB, numerically can be enormously valuable for a bunch of reasons. First off, there are often situations where no classic technique in differential equations or no simple mathematical structure that would just leap to the imagination comes to use. And you have some horrible, it's all numeric. Very useful and reason not even for the, how many of y'all are thinking about being theorists of some stripe or other? Okay, and how many of y'all are thinking about being experimentalists of some stripe or other? Okay, cool. So look, there's this deep prejudice in theory against numerical solutions of problems. It's myopia. It's a terrible attitude, and here's the reason. Computers are stupid. Computers are breathtakingly dumb. They will do whatever you tell them to do, but they will not tell you that that was a dumb thing to do. They have no idea. So in order to solve an interesting physical problem, you have to first extract all the physics and organize the problem in such a way that a stupid computer can do the solution. As a consequence, you learn the physics about the problem. It's extremely valuable to learn how to solve problems numerically, and we're going to have problem sets later on in the course in which you're going to be required to numerically solve some of these differential equations. It both is useful because you get numbers and you can check against some data, but also it lets you, in the process of understanding how to solve the problem, you learn things about the problem. So I want to mark that as a separate logical way to do it. So today I want to start by, our analysis by looking at a couple of examples of of solving the Schrödinger equation. And I want to start by looking at energy eigenfunctions. And then, once we understand how a single energy eigenfunction, how a single energy eigenfunction evolves in time, once we understand that solution of the Schrödinger equation, we're going to use the linearity of the Schrödinger equation to write down a general solution of the Schrödinger equation. Okay. So, first, what happens if we have a single energy eigenfunction? So, suppose our wave function, this function of x at time t equals 0, is in a known configuration, which is an energy eigenfunction phi sub e of x. What I mean by phi sub e of x is if I take the energy operator and I act on phi sub e of x, this gives me back the number e phi sub e of x. Okay? So it's an eigenfunction of the energy operator with eigenvalue e. So suppose our initial condition is that our system began life at time t equals 0 in the state with definite energy e. Recall that? First off, question. Suppose I immediately, at time 0, measure the energy of this system. What will I get? With what probability? 100%, because this is, in fact, of this form. It's a superposition of energy eigenstates, except there's only one term. And the coefficient of that one term is 1. And the probability that I measure the energy to be equal to that value is the coefficient norm squared, and that's 1 norm squared. Consider, on the other hand, if I take this wave function and I multiplied it by phase, e to the I alpha, what now is the probability, where alpha is just a number, what now is the probability that I measure the state to have energy e? It's still 1, because the norm squared of a phase is 1, right? Okay. The overall phase does not matter. So, suppose I have this as my initial condition. Let's take away the overall phase because my life will be easier. So here's the wave function. What is the Schrödinger equation? Well, the Schrödinger equation says that IH bar, time derivative of psi, is equal to the energy operator acting on psi. And I should be specific. This is psi at x at time t, can evaluate at this time 0, is equal to the energy operator acting on this wave function. But what's the energy operator acting on this wave function?
E sub E phi.
E. E on psi is equal to E on phi sub e, which is just E, the number. This is the number E, the eigenvalue, E times psi at x 0.
E times psi.
And now, instead of having an operator on the right hand side, we just have a number. So I'm going to write this difference equation slightly differently, i.e. time derivative of psi is equal to E upon IH bar, or minus I E over H bar psi. Yeah, recall that? This is the easiest differential equation in the world to solve. So the time derivative is a constant, well, times itself. That means that, sorry, I should write this here, therefore psi at x and t is equal to e to the minus I e t over h bar psi at x 0, where I've imposed the initial condition that at time t equals 0, the wave function is just equal to psi of x and 0. And in particular, I know what psi of x and 0 is. It's phi e of x. So I can simply write this as phi e of x. Recall that? So what this tells me is that under time evolution, a state which is initially in an energy eigenstate remains in an energy eigenstate with the same energy eigenvalue. The only thing that changes about the wave function is that its phase changes. And its phase changes by rotating with a constant velocity, e to the minus I, the energy eigenvalue, times time upon h bar. Now, first up, before we do anything else, as usual, we should first check the dimensions of our result to make sure we didn't make a goof.
All right, so I've been struggling with the dimensional analysis. So let me just do a little bit of quick ahead here, because this has been something that I have been not doing as well in the last few lectures. So what do we have here? Well, psi, as we know, should be 1 over root L, because the norm squared of that is the probability density function. So these should be 1 over L. dt is going to be This is the derivative of this respect to time. So this is going to be, let's just see, this is going to be 1 over, this is going to be 1 over t root L. And then this is h bar is equal to what? Length. Let's see, I need to, this is why I need to remember these. I want to say it's length times momentum, energy. How can we decompose energy here? Energy is, what is it? Length. It's length. Length force? No. That's a work. I don't know how this operator is going to work. All right. We're going to see what they say, but this is something definitely to work on later. I might have to do a Feynman technique
So,
quiz.
does this make sense dimensionally? Let's quickly check. Yeah, it does. So we have that the exponent there is ET over h bar.
ET over h bar.
Okay, and this should have dimensions of what in order to make sense? Nothing, exactly. It should be dimensionless. So what are the dimensions of h bar? Oh no, the dimensions, guys, not the units. What are the dimensions? It's an action, which is energy of time. So the units of the dimensions of h are an energy times a time, also known as a momentum times a position. Okay.
Okay, hold on a second. So this is P times X. Also an energy times the time. Yeah.
So this has dimensions of action or energy times time, and then upstairs we have dimensions of energy times time. So that's consistent. So this, in fact, is dimensionally sensible, which is good. Now, this tells you a very important thing. In fact, we just answered this question. At time t equals 0, what will we get if we measure the energy? E. At time t prime, some subsequent time, what energy will we measure? Yeah, does the energy change over time? Right, but when I say that, what I mean is, does the energy that you expect to measure change over time? No. Does the probability that you measure energy change? No, because it's just a phase, and the norm squared of a phase is 1. Yeah? Are we cool with that? Questions at this point? Okay, this is a very simple example. It's going to have a lot of power. Oh, yeah, question. Thank you. Excellent question. We will later, but not in 804 and 805. We'll discuss it in more detail. Nothing dramatic happens, but you just have to add more symbols. There's nothing deep about it. It's a very question. The question was, are we going to deal with energy operators that change in time? And my answer, well, okay. My answer was no, not in 804, but you will in 805. What you'll find is that it's not a big deal. Nothing particularly dramatic happens. We will deal with systems where the energy operator changes instantaneously. So not a continuous function, where at some moment we turn on an electric field or something like that. So we'll deal with that later on. But we won't develop a theory of energy operators that depend on time. But we could do it, and we'll do it in 805. There's nothing serious about it. Other questions? Okay, so these states, a state psi of x and t, which is of the form e to the minus I omega t, where omega is equal to e over h bar. This should look familiar. It's the derivative relation, whatever, times some phi e of x, where this is an energy eigenfunction. These states are called stationary states. And what's the reason for that? Why are they called stationary states? Let me erase this. Well, suppose this is my wave function as a function of time. What is the probability that at time t, I will measure the particle to be at position x, so probability density? Well, the probability density, we know from our postulates, it's just the norm squared of the wave function. This is psi at x t, norm squared. But this is equal to the norm squared of e to the minus phi omega t, phi e, by the Schrodinger equation. But when we take the norm squared, this phase cancels out, as we already saw. So this is just equal to phi e of x, norm squared, the wave, the energy eigenfunction norm squared, independent of time. So if we happen to know that our state is in an energy eigenfunction, then the probability density for finding the particle at any given position does not change in time. It remains invariant. The wave function rotates by an overall phase, but the probability density is the norm squared. It's insensitive to that overall phase, so the probability density just remains constant, whatever shape it is. Hence, it's called a stationary state. Notice this consequence. What can you say about the expectation value of the position as a function of time? Well, this is equal to the integral of dx in the state of psi of x and t. And I'll call this slice of e, just to emphasize. It's the integral dx, the integral over all possible positions, of the probability distribution, probability of x upon t times x. What this is equal to, the integral dx of phi e of x squared at x. But that's equal to expectation value of x at any time or time 0, p equals 0. Maybe the best way to write this is as a function of time. So the expectation value of x doesn't change. In a stationary state, expected positions, energy, these things don't change. Everyone cool with that? And it's because of this basic fact that the wave function only rotates by a phase under time evolution when the system is in an energy eigenvalue state. Questions? Okay. So here's a couple of questions for you guys. Are all states in energy? Are all systems always in energy eigenstates? Am I in an energy eigenstate? No, right? Okay, expected position of my hand is changing in time. I'm not in. So obviously, things change in time. Energies change in time. Positions, expected typical positions change in time. We are not in energy eigenstates. That's a highly non-generic state. So here's another question. Are any states ever truly in energy eigenstates? Can you imagine an object in the world that is truly described precisely by an energy eigenstate in the real world? Okay, there are a few knows why. Why not? Does anything really remain invariant in time? No, right? Everything is getting buffeted around by the rest of the universe. So not only are these not typical states, not only are stationary states not typical, but they actually never exist in the real world. So why am I talking about them at all? So here's why. And actually, I'm going to do this here. So here's why. The reason is this guy, the superposition principle, which tells me that if I have possible states, I can build superpositions of them. And this statement in Field linearity, which says that given any two solutions of the Schrödinger equation, I can take a superposition and build a new solution of the Schrödinger equation. So let me build it. So if I want to exploit the linearity of the Schrödinger equation, I do the following. Suppose psi, and I'm going to label these by n, psi n of x and t is equal to e to the minus I omega n t phi sub en of x, where en is equal to h bar omega n. And labels the various different energy eigenfunctions. So consider all the energy eigenfunctions phi sub en, and is a number which labels them. And this is the solution of the Schrödinger equation, which at time 0 is just equal to the energy eigenfunction of interest. Cool? So consider these guys. So suppose we have these guys such that they solve the energy eigenfunction, or the Schrödinger equation. Solve the Schrödinger equation. Suppose these guys solve the Schrödinger equation. Then, by linearity, we can take psi of x and t to be an arbitrary superposition, sum over n, c sub n, psi sub n of x and t. And this will automatically solve the Schrödinger equation by linearity of the Schrödinger equation. Yeah? Excellent. So if you could make a... So here's the question. The question is, look, a minute ago you said no system is truly in an energy eigenstate, right? But can we put a system in an energy eigenstate by just measuring the energy? Right? Isn't that exactly what the collapse postulate says? So here's my question. How confident are you that you actually measured the energy precisely? With what accuracy can you measure the energy? So here's the unfortunate truth. The unfortunate practical truth. I'm not talking about in principle things. I'm talking about in practice things in the real universe. When you measure the energy of something, you've got a box, and the box is a dial, and the dial is a needle, and it has a finite width, and your current meter is a finite sensitivity to the current. So you never truly measure the energy exactly. You measure it within some tolerance. And in fact, there's a fundamental bound. There's a fundamental bound on the accuracy with which you can make a measurement, which is just the following. And this is the analog of the uncertainty equation. We'll talk about this more later, but let me just jump ahead a little bit. Suppose I want to measure a frequency. So I have some signal, and I look at that signal for 10 minutes. Okay? Can I be absolutely confident that this signal is in fact a plane with the frequency that I just did? No, it could change outside that. But one point, there might have been small variations inside. There could have been a wavelength. It could change on a time scale longer than the time that I measured. So to know that the system doesn't change on an arbitrary that it's strictly fixed omega, I have to wait a very long time. And in particular, how confident you can be that the frequency is bounded by the time over which, so your confidence, your uncertainty in the frequency is bounded in the following fashion. Delta omega, delta t is always greater than or equal to 1, approximately. What this says is that if you want to be absolutely confident of the frequency, you have to wait an arbitrarily long time. Now, if I multiply this whole thing by h bar, I get the following. Delta E, so this is a classic equation of signals analysis. Delta E, delta t is greater than or approximately equal to h bar. This is a hallowed time energy uncertainty relation, which we haven't talked about. So, in fact, it is possible to make an arbitrarily precise measurement of the energy. What do I have to do? I have to wait forever. How patient are you? Right? So that's the issue. In the real world, we can't make arbitrarily long measurements. We can't isolate systems for an arbitrarily long amount of time. So we can't put things in a definite energy eigenstate by measurement. Did that answer your question? Great. How many people use the signals in this expression, the bound on the frequency? Oh, good. Okay, so we'll talk about that later in the course. Okay, so coming back to this. So we have our solutions of the Schrödinger equation that initially energy eigenstates. I claim I can take an arbitrary superposition of them by linearity, derive that this is also a solution of the Schrödinger equation. Okay. And in particular, what that tells me is, another way to say this is that way to say this is that if I know that sine of x and times 0 is equal to sum over n, so if sine of x, if the wave function at some particular moment in time can be expanded as sum over n cn phi e of x, if this is my initial condition, my initial wave function is some superposition, then I know the wave function is a subsequent time, so the wave function by superposition, psi of x and t, is equal to sum over n cn e to the minus I omega n t phi n. Sorry, this should be phi to n phi n of x. Okay. And I know this has to be true because this is a solution of the Schrödinger equation by construction, and at time t equals 0, it reduces to this. So this is a solution of the Schrödinger equation satisfying this condition at the initial time t equals 0. Cool. Don't even have to do a calculation. So having to solve the Schrödinger equation once for energy eigenstates allows me to solve it for a general superposition. However, what I just said isn't quite enough. I need one more argument. And that one more argument is really the stronger version of 3 that we talked about before, which is that given an energy operator, the equation once for energy eigenstates allows me to solve it for a general superposition. However, what I just said isn't quite enough. I need one more argument. And that one more argument is really the stronger version of 3 that we talked about before, which is that given an energy operator, E, we find the set of wave functions finds the eigenfunctions of the energy operator with eigenvalue E. So given the energy operator, we find its eigenfunctions. Any wave function psi at x, let's say times 0, any function of x can be expanded as a specific superposition, sum over n cn phi e sub n of x. Okay. And if any function can be expanded as a superposition of energy eigenfunctions, and we know how to take a superposition, an arbitrary superposition of energy eigenfunctions, and find the corresponding solution of the Schrödinger equation, what this means is we can take an arbitrary initial condition and compute the full solution of the Schrödinger equation. All we have to do is figure out what these coefficients cn are. Ever cool that? So we have thus, using superposition and energy eigenvalues, totally solved the Schrödinger equation and reduced it to the problem of finding these expansion coefficients. Meanwhile, these expansion coefficients have a meaning. They correspond to the probability that we measure the energy to be equal to the corresponding energy, E sub n. And it's just the norm squared of that coefficient. So those coefficients mean something.
Okay, I'm just going to pause this and write down this train of logic that he had here because this is important. So he's saying that we have the Schrödinger equation. We can, all right, break it into energy eigenfunctions. And this is just because of superposition and linearity that we can do this. Breaking it, these are also these are stationary states. States, they only rotate by a phase. And then once we take all of these energy eigenfunctions, what we're essentially doing is, if we know the likelihood of each energy state, we can determine the coefficients for superimposing all of the eigenfunctions. So we can add it all up.
And they allow us to solve the problem. Cool? So this is fairly abstract. So let's make it concrete by looking at some examples. So just as a quick aside, this should sound an awful lot like the Fourier theorem. And let me comment on it. This statement originally was about a general observable and general operator. Here we're talking about the energy. But let's think about a slightly more special example, or more familiar example. Let's consider momentum. In momentum, we can find a set of eigenstates. What are the set of good, properly normalized eigenfunctions of momentum? What are the eigenfunctions of momentum operator? E to the ik. kx, exactly. And if you know 1 over root 2 pi, e to the I kx. Okay. So I claim that for every different value of k, I get a different value of p, and the eigenvalue associated to this guy is p is equal to h bar k. That's the eigenvalue. And we get that by acting with the momentum, which is h bar upon I. H bar upon times derivative with respect to x. Derivative with respect to x pulls down an I, k times the same thing. H bar multiplies the k over I, kills the I, and leaves us with an overall coefficient of h bar k. This is an eigenfunction of the momentum operator with eigenvalue h bar k. And that statement, 3, is the statement that an arbitrary function f of x can be expanded as a superposition of all possible energetic limits, but k is continuously valued. Any momentum, so that's an integral dk. 1 over root 2 pi. E to the I kx times some coefficients. And these coefficients are labeled by k, but since k is continuous, I'm going to call it a function. And just to give it a name, instead of calling it c sub k, I'll call it f tilde of k. This is of exactly the same form. Here is the expansion. There's the eigenfunction. Here is the eigenfunction. Here is the expansion coefficient. Here's the expansion coefficient. And this has a familiar name. It's the Fourier theorem. So we see that the Fourier theorem is this statement, statement 3, the superposition principle, for the momentum operator. We also see that it's true for the energy operator. And
so let me just write that down. Fourier theorem is superposition principle for momentum.
what we're claiming here is that it's true for any observable. Given any observable, you can find its eigenfunctions, and they form a basis on the space of all good functions, and an arbitrary function can be expanded in that basis. So, as a last example, consider the following. We've done energy, we've done momentum. What's another operator we care about? What about position? What are the eigenfunctions of position?
The deltas.
X hat on delta of x minus y is equal to y delta of x minus y.
So one thing I'm not entirely sure at here is how the energy operator is also a Fourier transform. It's just with time instead of x. No, I think that's true. I'm just gonna put that as a little hypothesis. I like to put when I'm guessing in the notes separate from the actual notes, so I don't like get confused later. So, but it's good to write these things down just so you can clarify your thoughts. Ft in x is momentum eigenstates, and Ft in time energy eigenstates. Is that right? What do we have here for the? I mean, yeah, this is the, where did I write down the, yeah, here, this is the stationary states, or these are also complex exponentials. They're just rotating with time as opposed to space. So we have things that are going like this in time, and we have curves that are spatial curves.
It multiplies by the variable x, but it's 0 except that x is y, so it's x by y. So there are the eigenfunctions, and this statement is a statement that we can represent an arbitrary function f of x in a superposition of these states of definite x. F of x is equal to the integral over all possible expansion coefficients dy delta of x minus y times some expansion coefficient. And what's the expansion coefficient? It's got to be a function of y, and what function of y must it be? Just f of y, because this integral against this delta function had better be f of x, and that will only be true if this is f of x. Okay? So here we see, in some sense, the definition of the delta function, but really, this is a statement of the superposition principle. The statement that any function can be expanded as a superposition of eigenfunctions of the position operator. Any function can be expanded as a superposition of eigenfunctions of momentum. Any function can be expanded as a superposition of eigenfunctions of energy. Any function can be expanded as a superposition of eigenfunctions of any operator of your choice. Okay? The special case is the Fourier theorem. The general case is the superposition postulate. Cool? Powerful tool. And we've used this powerful tool to write down a general expression for a solution of the Schrödinger equation. That's good. That's progress. So let's look at some examples of this. So our first example is going to be for the free particle. So a particle whose energy operator has no potential whatsoever. So the energy operator is going to be just equal to p squared upon 2n kinetic energy. Yeah.
When you say, any wave function can be expanded in terms of
Energy function.
yes, does the eigenvalues have come from an operator corresponding to observable?
Yes, absolutely. I'm starting with that assumption. We'll give, so again, this is a first pass of the axioms of quantum mechanics. We'll make this more precise, and we'll make it more general later on in the course as we go through a second iteration of this. And there we'll talk about exactly what we mean by operators or perfect operators. But for the moment, the sufficient and physically correct answer is operators corresponding to observable values. Yeah. That's an excellent question. In general, no. So here's the question. The question is, look, if this is true, should it be that the eigenfunctions, since our basis for the good functions, are inside the space of reasonable functions? they should also be reasonable functions, right? So, if you're going to expand, for example, insert two-dimensional vector space, you want to say any vector can be expanded in a basis of pairs of vectors in two dimensions, right? Like x and y. You really want to make sure that those vectors are inside your vector space. But if you say this vector in this space can be expanded in terms of two vectors, this vector and that vector, you're in trouble, right? That's not going to work so well. So you want to make sure that your vectors, your basis vectors, are in the space. For position, the basis vector is a delta function. Is that a smooth, continuous, and normalizable function? No. For momentum, the basis functions are plane waves that extend off to infinity and have support everywhere. Is that a normalizable, reasonable function? No. So both of these sets are really bad. So at that point, you might say, look, this is clearly nonsense. But here's the important thing. Well, it's true that so this is a totally mathematical aside for those of you who don't care about math, don't worry about it. Well, these guys don't technically live in the space of non-stupid functions, reasonable, smooth, normalizable functions. What you can show is that they exist in the closure, the completion of that space. Okay? So you can find a sequence of wave functions that are good wave functions, an infinite sequence that eventually that infinite sequence converges to these guys, even though these are silly. So for example, for the position eigenstates, the delta function is not a continuous smooth function. It's not even a function, really. It's some god-awful thing called a distribution. It's some horrible thing. It's the thing that tells you, give it an interval, I'll give you a number or a function. So, but how do we build this as a limit of totally reasonable functions? We've already done that. Take this function with area 1. And if you want, you can round this out by making a hyperbolic tangents. Okay? And, we did that on one of the problem sets. Okay? And then just make it more narrow and more tall. And keep it more narrow and more tall, more narrow and more tall, keeping its area to be 1. And I claim that eventually that series, that sequence of functions converges to the delta function. So it's not technically in our space. It's in the completion of our space. In the sense that we take a series and they converge to it. And that's what you need for this theorem to work out. That's what you need for the Fourier theorem. And in some sense, that observation was really the genius of Fourier, understanding that could be. That was a totally mathematical side. That answer your question? Okay. Every once in a while, I can't resist talking about these sort of details because I really like them. But they're also, it's good to know that stupid things like this can't matter for us, and they don't. But it's a very good question. If you're confused about some mathematical detail, no matter how elementary, ask. If you're confused, someone else in the room is also confused. So please don't hesitate. Okay, so our first example is going to be the free particle. And this operator can be written in a nice way. We can write it as minus, so p squared is, p is h bar upon I dx, so this is minus h bar squared upon 2m, two derivatives with respect to x. There's the energy operator. So we want to solve for the wave functions. So let's solve it using an expansion in terms of energy eigenfunctions. So what are the energy eigenfunctions? We want to find.
Okay. Start a new page here. You'll note that I'm going fast, and then I like to pause it at times. So I find this is more efficient because you can see there's like parts where he's just sort of answering questions that, they're kind of interesting, but they're not necessarily stuff that I have to master. And then there's other times where he'll skim over a point, which is kind of going over my head. So I'm not pausing when maybe you would pause, but you can understand this principle if you were to go through the class yourself.
Functions e on phi sub e, such that this is equal to, whoops, that's not a vector, that's a hat, such that this is equal to a number e phi sub e. But given this energy operator, this says that minus h bar squared over 2m, so that's 2.
I better
2m,
write them consistently.
Phi prime prime of x is equal to e phi of x, or equivalently, phi prime prime of x plus 2me over h bar squared phi of x is equal to 0. Okay, so I'm just going to call 2me because it's annoying to write it over and over again over h bar squared. Well, first off, what are its units? What are the units of this coefficient? Well, you can do it two ways. You can either do dimensional analysis of each thing here, or you can just note that we started with a dimensionally sensible equation, and this has units of this divided by length twice. Right? So this must have units of 1 over length squared. So I'm going to call this something like k squared, something that has units of 1 over length squared. And the general solution of this is that phi, e of x, well, this is a second order differential equation. It will have two solutions with two expansion coefficients, a e to the ikx plus b e to the minus ikx. A state with definite momentum and definite negative momentum, where such that e is equal to h bar squared k squared upon 2m. And we get that just from this. Okay, so this is the solution of the energy eigenfunction equation. Just a note of terminology, people sometimes call the equation determining an energy eigenfunction the energy eigenfunction equation. Sometimes that's referred to as the Schrödinger equation. That's a sort of cruel thing to do to language, because the Schrödinger equation is about time evolution, and this equation is about energy eigenfunctions. Now, it's true that energy eigenfunctions evolve in a particularly simple way under time evolution, but it's a different equation. This is telling you about energy eigenstates. Okay. Okay, and then there are more discussion of this is done in the notes, which I will leave aside for a moment. But I want to do one more example before we take off. Wow, we got through a lot less than expected today. And the one last example is the following. It's a particle in a box. And this is going to be important for your problem set, so I'm going to go ahead and get this one out of the way as quickly as possible. So, example 2. Particle in the box. Okay. So what I mean by particle in a box is I'm going to take a system that has a deep well. Okay, so what I'm drawing here is the potential energy U of x. Where this is some energy E naught, and this is the energy 0, and this is the position x equals 0, and this is the position x equals L. And I'm going to idealize this by saying, look, I'm going to be interested in low energy physics, so I'm going to just treat this as infinitely deep, and meanwhile, my life is easier if I don't think about curvy bottoms, but I just think about things as being constant. So my idealization is going to be that the well is infinitely high and square. Okay. So out here, the potential is infinite. And in here, the potential is 0. U equals 0 inside between 0 and L for x. Okay. So that's my system particle in a box. So let's find the energy eigenfunctions. And again, it's the same differential equation as before. So first off, before we even solve anything, what's the probability that I find x less than 0 or find the particle at x greater than L? Right, because the potential is infinitely large out there. It's just not going to happen. If you found it there, that would correspond to a particle with infinite energy, and that's not going to happen. So this tells us effectively a boundary condition, psi of x is equal to 0 outside the box. So all we have to do is figure out what the wave function is inside the box between 0 and L. And meanwhile, what must be true of the wave function at 0 and at L? It's got to actually vanish at the boundary. So this gives us boundary conditions outside the box and at the boundaries, x equals 0, x equals L. Okay, but what's our differential equation inside the box? Inside the box, well, the potential is 0. So the equation is the same as the equation for a free particle. It's just this guy. And we know what the solutions are. So the solutions can be written in the following form. Therefore, inside the wave function, oops, let me write this as phi sub b. Phi sub b is a superposition of 2, and instead of writing it as exponentials, I'm going to write it as sines and cosines, because you can express them in terms of each other. Alpha cosine of x, kx, plus beta sine of kx, where again alpha and beta are general complex numbers. But we must satisfy the boundary conditions imposed by our potential at x equals 0 and x equals L. So from x equals 0, we find that phi must vanish when x equals 0. When x equals 0, this is automatically 0. Sine of 0 is 0. Cosine of 0 is 1. So that tells us that alpha is equal to 0. Meanwhile, the condition that at x equals L, the wave function must also vanish, tells us that, so this term is gone, if we set alpha to 0. This term, when x is equal to L, had better also be 0. Well, we could solve that by setting beta equal to 0, but then our wave function is just 0, and that's a really stupid wave function. So we don't want to do that. We don't want to set beta to 0. Instead, what must we do? Well, we've got a sine, and depending on what k is, it starts at 0 and it ends somewhere else, but we need it to hit 0. So only for a very special value of k will it actually hit 0 at the end of L. We need KL equals 0. But really, KL is a multiple of pi. KL is equal, and we want it to not be 0, so I'll call it n plus 1, an integer, times pi. Or equivalently, k is equal to sub n is equal to n plus 1, where n goes from 0 to any large positive integer, pi over L. Okay, so the energy eigenfunctions here, the energy eigenfunction is subnormalization, a sub n sine of k and x. Okay. And where kn is equal to this, and as a consequence, E is equal to h bar squared kn squared. E sub n is h bar squared kn squared over 2m, which is equal to h bar squared, just plugging in I squared, n plus 1 squared over 2ml squared. Okay. And what we found is something really interesting. What we found is, first off, that the wave functions look like, well, the ground state, the lowest possible energy there is n equals 0. For n equals 0, this is just a single half a sine wave. It does this. This is the n equals 0 state. And it has some energy, which is E0. And in particular, E0 is 0 is equal to h bar squared, pi squared, over 2ml squared. I.e., it is impossible for a system to have, it is impossible for a particle in a box to have an energy lower than some minimal value, E naught, which is not 0. You cannot have less energy than this. Everybody agree with that? There is no such eigenvalue with energy less than this. Meanwhile, it's worse. The next energy is when n is equal to 1, because if we increase the wavelength, or if we decrease the wavelength or increase k a little bit, we get something else like this, and that doesn't satisfy our boundary condition. In order to satisfy our boundary condition, we have to eventually have it cross over and get to 0 again. And if I can only draw, I'll draw it up here. It looks like this. And this has an energy E1, which you can get by plugging 1 in here. And that differs by 1, 2, 4, a factor of 4 from this guy. E1 is 40, 0. And so on and so forth. The energies are gapped. They're spread away from each other. The energies are discrete. And they get further and further away from each other as we go to higher and higher energies. So this is already a peculiar fact. And we'll derive and explore some of its consequences later on. But here's something I want to emphasize for you. Already, in the first, most trivial example of solving the Schrödinger equation, or actually even before that, just finding the energy eigenvalues and energy eigenfunctions of the simplest system you possibly could, either a free particle or a particle in a box, a particle trapped inside a potential well. What we discovered is that the energy eigenvalues, the allowed values of the energy, are discrete. And that they're greater than 0. You can never have 0 energy. And if that doesn't sound familiar, let me remind you of something. The spectrum of light coming off of a gas of hot hydrogen is discrete. And no one's ever found a 0 energy beam of light coming out of it. And we're going to make contact with that experimental data. That's going to be part of the job for the rest. See you next time.
All right, so what did we cover in this class? So in particular, this class was a little bit of a review, and then it was all about energy eigenstates and how we can represent any of our functions in energy eigenstates. And that's useful because each of the energy eigenstates themselves are stationary. And so if we understand these stationary eigenstates that are only rotating in a phase, that they're not actually changing or evolving over time, we can build out our functions out of that. And then that's easy to solve this differential equation, this first order differential equation that is the Schrödinger equation. And in particular, we looked at two different cases here. One of them was the free particle condition, where it just sort of generically has these components of momentum in either direction. And then an interesting result came is that if we look at the well condition, so an infinite well, there are only discrete values that the wave can happen because it has to hit 0 at the edges. And if you have a smooth wave, there is only, only so many places that it can fit. So this is kind of an interesting result. Let's just sort of take a bit of an assessment at how do I feel about these things. Again, we're getting in lecture 6. We're getting a little bit further from doing the practice problem. So this is always an issue of you go too far in the lectures and it's harder to fully understand it because you haven't done the work of doing the practice problems. And in the actual MIT class, they would have probably already done about 3 problem sets by now. The converse of this, and what I did in the MIT challenge, was do the entire lectures first, because then you get a real sense of where you have difficulties, what you need to learn, what you don't need to learn. You get that overall picture. And so I'm kind of split in the middle here, and I'm going to lecture 10 before I do the problem sets, because I think I can still, I still have a good understanding of what's going on. I still am grokking what he's doing. It's not as if when he's doing math, it's just going completely over my head, although sometimes he's doing it with a, well, obviously this, and it's not as obvious to me. So there's some examples here. Where did we do we did some, so dimensional analysis. I have already proven that I'm not very good at the dimensional analysis, so this is definitely something I'm going to want to work on. Obviously, it makes sense. I think I need to get a little bit better at what are all the fundamental constants, what are all the different types of things we're looking at, how do all the units relate to each other, because, obviously that energy times time is the same as momentum times length is not obvious to me. Like I might be able to work that out, but that was something he kind of just in the class was like, well, obviously ET is the same as PX, so we can just say that this is dimensionless. All right. What else? I think this is pretty good. I mean, one of the things he points out in doing differential equations, and I remember this from doing differential equations in 1803, similarly to how when you go from doing differentiation to integration, differentiation is just a shut up and calculate kind of procedure. You can always find the derivative of something, whereas integration is a backtracking process. It's what would have been the function that this would have been the derivative of. And unfortunately, that's not always super easy to solve. Sometimes it actually requires a lot of tricks, a lot of calculus, a lot of mathematical insight. Now, differential equations are kind of that variety that sometimes the format they're in, you can exploit how they're formatted to solve them really easily. So one of the reasons for that, for doing these energy eigenfunctions, is that we have these very simple differential equations that we can solve. But other times it could be set up in such a way that it is perhaps even impossible to solve analytically. So he suggested kind of these three methods: the brute force, cleverness, and numerical solutions. Again, I think this is I'm pretty good with this stuff. You'll notice in my notes right here, I put down a 5233. This is because I was doing this and he kind of sped over a little bit of the algebra. I didn't feel like it was worth stopping to go through meticulously, but I leave these little timestamps whenever something was discussed and I don't feel like I understood it when I was taking my notes completely. And the question is, sometimes I'm stopping to redo things. Sometimes I'm just, okay, I'll mark this down and go ahead, because sometimes the confusion gets cleared up later. Like you do some problems and you're like, oh yeah, that's obvious. I didn't get that at the time, but it's obvious. And then other times it's like, okay, no. I need to understand what's going on here if I'm going to understand any of the lecture. So here he was kind of transitioning from topics, and I was like, you know what, I'm not going to go through all this. So I'm just going to put this timestamp. So if I want to go back and learn it later. Now, I'm going to just rush ahead and go on to lecture 7 because I'm not going as fast as I was hoping I was going to go. Part of that's like I'm doing this. Part of the goal of this was to do it at a little bit more leisurely pace. I mean, when I was doing the MIT challenge, the goal was usually to get done 10 lectures in a day. I mean, we're nearing the end of day 2 and I'm on lecture 7, so I'm definitely not going at that pace. But on the other hand, I'm also trying to get a little bit more depth in each class. I'm doing a bit more active recall, doing a bit more note-taking, pausing, doing that kind of thing. Whereas during the MIT challenge, I was often willing to accommodate that there were gaps in my understanding and just to get through all of it so that I could be maximally efficient. So this is, I think, a little bit more the approach I would recommend today to someone who's going through a typical class, especially one of difficulty like this. So I'm going to jump on to lecture 7. I'm hoping it's 10 to 3 right now. I haven't actually been going at 1.5 times the speed for that much of it. So we'll see. We'll see. My hope is that, again, let's get to lecture 10. Let's get lecture 10 under our belt. I'd like to do it by tomorrow morning if I can. And then I can really have a nice 2.5 days to get into the practice problems, which, if I'm being honest, that's a big part of learning the course. And so this will sort of be definitely keeping us on track for having more time for really like getting into things, playing with the equations. So I'm not just sitting here watching videos the whole time. Although I do really like Alan Adams as a lecturer. I think his passion for it really comes through. And so I always like watching people who are really excited about what they're talking about, what they're teaching. So let me jump forward and let's try loading number 7.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from visit MIT OpenCourseWare at ocw.mit.edu.
Okay, so I want to start out by reviewing a few things. I'm putting some machinery together. Unfortunately, this thing is sort of stuck. We're going to need it later, so I don't know. I'll put it up for now. So first, just a bit of notation. This symbol, you should think of like the dot product or the arrow product. It's just saying that bracket FG is the integral. It's a number that you get. So this is a number that you get from the function f and the function g by taking f, taking its complex conjugate, multiplying it by g, and then integrating over all positions.
All right, let me write that down. That's going to be important. You know, it's funny. He's putting the dx first. Whenever I did it in calculus in the previous classes, they always put the dx at the end, and this just, to me, just makes way more sense. I don't know if this is normal notation for physicists or something, but I would always forget to put the dx on my equations.
Right? So it's a way to get a number. And you can think about it as the analog for functions of the dot product for vectors. It's a way to get a number out of two vectors. And so, for example, with vectors, we can do v dot w, and this is some number, and it has a nice property that v dot v, you can think of as v squared, it's something like a length. It's strictly positive, and it's something like a length of a vector. Similarly, if I take f and take its bracket with f, this is equal to the integral dx of f squared, and square f could be complex, so f norm squared. This is strictly non-negative, it could vanish, but it's not zero at a point. It's not negative at a point, it's the norm squared. So this will be zero if and only if what? F is zero, f is the zero function, right? So the same way that the vector, if you take a vector and you take its dot product with itself, take norm, it's zero if and only if the vector is zero. So this piece satisfies a lot of the properties of a dot product. You should think about it as Morley equivalent. We'll talk about that in more detail later. Second, basic postulate of quantum mechanics, every observable is associated with an operator, and it's an operator acting on the space of functions or on the space of wave functions. And to every operator corresponding to an observable in quantum mechanics are associated a special set of functions called the eigenfunctions, such that when the operator acts on that function, it gives you the same function back times a constant. What these functions mean physically is they are the wave functions describing configurations with a definite value of the corresponding observable. If I had an eigenfunction position with eigenvalue x naught, awesome. Thank you, AD person. Thank you. So if your system is described by a wave function, which is an eigenfunction of the with eigenvalue x naught, that means you can be confident that the system is in a configuration corresponding to having a definite position x naught. Right? It's not a superposition of different positions. It is at x naught. Similarly, momentum. Momentum has eigenfunction. And we know these guys are. These are the exponentials. EV the axis. So the eigenfunction, and those are the wave functions describing states with definite value of the momentum, the associated observable. Energy as an operator. Energy is described by an operator which has eigenfunction called phi sub n. With energies e sub n, those are the eigenvalues. And if I tell you that your wave function is the state phi sub 2, what that tells you is that the system has a definite energy e sub 2 corresponding to that eigenvalue. Cool. And this is true for any physical observable, but these are sort of the basic ones that we'll keep focusing on: position, momentum, energy for the next while. Okay. Now, a nice property about these eigenfunctions is that for different eigenvalues, the associated wave functions are different functions. What I mean by saying they're different functions is they're actually orthogonal functions in the sense of this dot product. If I have a state corresponding to be at x0, definite position x0, that means I have an eigenfunction of position with eigenvalue x0, and I have another that corresponds to being at x1, an eigenfunction of the position operator with eigenvalue x1, then these wave functions are orthogonal to each other. I can be at 0 if x0 is not equal to x1. Can we call that? Now, meanwhile, not only are they orthogonal, but they're normalized in a particular way. The inner product gives me a delta function, which goes beat once. So that if I integrate against it, I get 1. Same thing with momentum. You do this, you're checking on the problem set. I don't remember if it was the last one or this one. And for the energies, and energy 1, if I know the system is in state energy 1, and well, let's say E sub n and E sub m, those are different states if n and m are not equal to each other. And this inner product is 0 if n and m are not equal to each other, and 1 if they are properly normalized.
What are we looking at here? So if we go x0, x1, okay, x prime, this is also x equal to
Ever go there? Yeah. Absolutely. It's absolutely possible for two eigenfunctions to have the same eigenvalue. That is certainly possible. Yeah, good. So here's thank you. This is a good technicality that I didn't want to get into, but we'll go ahead and get into it. It's a very good question. So the question is it possible for two different eigenfunctions to have the same eigenvalue? Could there be two states with the same energy? Different states, same energy. Yeah, that's absolutely possible. We'll run into that. And there's nice physics included in it. Well, let's think about what that means. But the subsequent question is, well, if that's the case, are they really still orthogonal? And here's the crucial thing. The crucial thing is, let's say you take one function. I'll call the function f1 or phi1. Consider phi1 and let it have energy e1, so that e acting on phi1 is equal to e1 phi1. Okay, and let there be another function phi2, such that the energy operator acting on phi2 is also equal to e1 phi2. These are said to be degenerate. Degenerate doesn't mean you go out and trash your car. Degenerate means that the energies are the same. Okay, so what does this tell me? This tells me a cool fact. If I take a wave function, phi, and I'll call this phi star, in honor of Sri Kulkarni. So I've got this phi star, which is a linear combination alpha, phi 1 plus beta, phi 2. A linear combination that a superposition of those two states. Is this also an energy acting function? Yeah, because if I add on E on phi star with E, then it's linear. So E acting on phi star is E acting on alpha phi 1. Alpha is a constant, doesn't care. Phi 1 gives me an E1. Similarly, E acting on phi 2 gives me an E1. So this is equal to, if I act with E on this guy, this is equal to, from both of these, I get an overall vector of E1. So notice that we get the same vector back times a constant. A common constant. So when we have degenerate eigenfunctions, we can take arbitrary linear combinations that then get another degenerate eigenfunction. Cool? So this is like, imagine I have a vector and I have another vector, and they share the property that they're both eigenfunctions of some operator, then he's any linear combination that is also. Right? So there's a whole vector space, there's a whole space of possible functions that all have the same eigenvalue. So now you say, well, look, are these two orthogonal to each other? No, these two, no. But here's the thing, if you have a vector space, you have a space, you always find orthogonal guys, and a basis for that space. Yes? So while it's not true that the eigenfunctions are always orthogonal, it is true. We will not prove this, but we will discuss the proof of it later by pulling the mathematician out of the closet. The proof will say that it is possible to find a set of eigenfunctions which are orthogonal in precisely this fashion, even if they're degeneracies. Okay, that theorem is called the spectral theorem, and we'll discuss it later. So it is always possible to do so, but you must be alert that there may be degeneracies. There aren't always degeneracies. In fact, degeneracies are very special. Why do two numbers happen to be the same? Something has to be forcing them to be the same. That's going to be an important theme for us. But it certainly is possible. Good question. Other questions? Yeah. Yeah, so using the triangular brackets so there's another notation for the same thing, which is FG, but this carries some slightly different weight. It means something, you'll see this in books, and this means something very similar to this. I'm not going to use this notation, it's called Dirac notation. We'll talk about it later in the semester, we're not going to talk about it just yet. When we see this, it means, effectively, it means the same thing as this. This is sort of like dialect, it's like French and Quebecois. Other questions? My wife's Canadian. Other questions? Okay. So given the fact that we can associate observables to operators come with special functions, the eigenfunctions, those eigenfunctions corresponding to have a definite value of the observable, and they're orthonormal. This tells us, and this is really the statement of the spectral theorem, that any function can be expanded in a basis of states with definite values of some observable. So for example, consider position. I claim that any wave function can be expanded as a superposition of states with definite position. So here's an arbitrary function, here's a set of states with definite position, the delta functions, and I can write any function as a superposition with some coefficients of states with definite position, integrating over all possible positions x naught. Yeah. And this is also sort of trivially true, because what's this integral? Well, it's an integral dx naught over all possible positions of the delta function. But we're evaluating at x. So this is 0 unless x is equal to x naught. So I'm just putting in x instead of x naught, and that gives me side x. Sort of tautological. We do the same thing for momentum eigenfunctions. I claim that any function can be expanded in a superposition of momentum eigenfunctions, where I sum over all possible values of the momentum with some weight. Right? Where this side tilde of k is just telling me how much amplitude there is at that wave number. Cool? But this is a Fourier theorem. It's a Fourier expansion. So purely mathematically, we know that this is true. Okay? But there's also the physical statement. Any state can be expressed as a superposition of states with definite momentum. There's math in here, but there's also physics. Finally, this is less obvious from a mathematical point of view, because that even tells you what energy is. Any wave function can be expanded in states with definite energy. So this is a state, my state En, with definite energy, with some coefficient summed over all possible values of the energy. Okay? Given any physical observable, momentum, position, angular momentum, whatever, given any physical observable, a given wave function can be expanded as some superposition of having definite values of that. Will it in general have definite values of the observable? Will a general state be an energy eigenfunction? No, but any state is a superposition of energy eigenfunctions. Will a definite state, or will a random state have definite position? Certainly not. You can have this wave function, right? Superposition. Yeah.
Why is energy special such that you can make an arbitrary state with a countable number of energy eigenfunctions that happens to a continuous factor?
Excellent question. So that phrase that slightly differently. It's an excellent question. We'll come to that at the end of today's lecture. So the question is this: those are integrals. That is a sum over discrete things. Why? Why is the possible values of position continuous, possible values of momentum continuous, and possible values of energy discrete? The answer to this will become apparent over the course of your next few problem sets. You have to do some problems to get your fingers dirty to really understand this. But here's the statement, and we'll see the first version of this at the end of today's lecture. Sometimes the allowed energies of the system, the energy eigenvalues, are discrete. Sometimes they are continuous. They will be discrete when you have bound states, states that are trapped in some region and aren't allowed to get arbitrarily far away. They will be continuous when you have states that can get arbitrarily far away. Sometimes the momentum will be allowed to be discrete values, sometimes it will be allowed to be continuous values, and we'll see exactly why. But the thing I want to emphasize is that I'm writing this to emphasize that it's possible that each of these can be discrete or continuous. The important thing is that once you pick your physical system, you ask what are the allowed values of position, what are the allowed values of momentum, and what are the allowed values of energy. And then you sum over all possible values. Now, in the examples we looked at yesterday, or last lecture, the energy could have been discrete, as in the case of the infinite well, or continuous, as in the case of the free particle. In the case of a continuous particle, this would have been an integral. In the case of a system such as the free particle where the energy containing a continuous number of possible values, this would be a continuous integral. To deal with that, I'm often going to use the notation, just shorthand, integral sum, which I know is a horrible bastardization of all this code just, but on the other hand, emphasizes the fact that in some systems you will get continuous, in some systems discrete, and sometimes you'll have both continuous and discrete. For example, in a hydrogen. In hydrogen, we'll find that there are bound states where the electron is stuck to the hydrogen nucleus, to the proton. And there are discrete allowed energy levels for that configuration. However, once you ionize the hydrogen, the electron can have any energy you want. It's no longer bound. It can just get arbitrarily far away. And there are an uncountable infinity of continuous set of possible states. So in that situation, we'll find that we have both a discrete and a continuous series of possible states. Yeah? Yeah, sure, if you work on labs. So for example, consider the following quantum system. I have an undergraduate, and that undergraduate has been placed in one of 12 boxes. Okay? Now, what's the state of the undergraduate? I don't know. Is it a definite position state? It might be, but probably it's a superposition, an arbitrary superposition, right? But very impressive undergraduates at MIT. So, okay, other questions? Yeah. Excellent question. We'll come back to that. Very good question. Leading question. Okay, so we have this. The next thing is that energy eigenfunctions satisfy some very special properties. Right? And in particular, energy eigenfunctions have the property from the Schrödinger equation, I h bar dt on psi of x and t is equal to the energy operator acting on psi of x and t. This tells us that if we have psi of x naught on t0 is equal to phi n of x, as we saw last time, then the wave function psi x at time t is equal to phi n of x, and it only changes by an overall phase. E to the minus I e n t over h bar. And this ratio en upon h bar will often be written omega, n is equal to en over h bar. This is just the de Broglie relations. Okay? Everyone cool with that? So our energy eigenfunctions, are how to say, no two possible wave functions are, no wave function is more morally good than another, but some are particularly convenient. Energy eigenfunctions have the nice definite position, they don't necessarily have definite momentum, they do evolve over time in a particularly simple way. Okay? And that allows me, that and the superposition principle, allow me to write the following. If I know that this is my wave function at psi at x at time 0, okay, so let's say in all these cases this is psi of x at time 0, how does this state evolve forward in time? It's kind of complicated. How does this description, how does psi tilde of k evolve forward in time? Again, kind of complicated, but when I express in terms of the energy eigenstates, the answer to how it evolves forward in time is very simple. Because I know that this is a superposition, a linear combination of states with definite energy. States with definite energy evolve with a phase, and the Schrödinger equation is linear. So solutions of the Schrödinger equation add to become solutions of the Schrödinger equation. So how does this state evolve forward in time? It evolves forward with a phase. 2 lines omega nt, 1 for every different term to sum. Cool? So we are going to harp on energy eigenfunctions not because they're more moral or more just or more good, but because they're more convenient for solving the time evolution problem in quantum mechanics. So most of today is going to be about this expansion and qualitative features of energy eigenfunctions. Cool? Okay. And just to close that out, let's think of, I just want to remind you of a couple of examples that we did last time, just get them on board. So the first is a free particle. So for free particle, we have that our wave functions of psi n are equal to a, well, actually, let me not write that down. Actually, let me see more the free particle because it's so trivial. Let me just talk about the infinite well. Okay, so the potential is infinite out here, and it's 0 inside the well. It goes from 0 to L. This is just my choice of notation. And the energy operator, as usual, is p squared on 2m plus u of x. You might say, where did I derive this? And the answer is I didn't derive this, I just wrote it down. It's like force in Newton's equations. You just declare some force, and you ask, what system does it model? So here's my system. It has what looks like a classical kind of energy, except the all objects. And the potential here is this guy. It's 0. And between 0 and L, it's infinite elsewhere. And as we saw last time, the solutions to the energy eigenvalue equation are particularly simple. Phi sub n of x is equal to root, properly normalized 2 upon L, sine of k n x, where k n is equal to n plus 1 pi, right, as an integer, upon L. And these were chosen to satisfy boundary conditions. The wave function was vanished here, hence a sine, and k was chosen so that it turned over and just hit 0 as we got to L. And that gave us that the allowed energies were discrete because the E, and which you can get by just plugging into the energy eigenvalue equation, was equal to h bar squared k n squared upon 2m. So this tells us a nice thing. First off, in this system, if I take a particle and I throw it in here in some arbitrary state, so that at time t equals 0, the wave function x is 0 is equal to psi over n cn, oh sorry, let me write this as phi n of x cn. Okay, can I do this? Can I just pick some arbitrary function which is a superposition of energy eigenstate? Sure, because any function is. Any function can be functions. And so this tells us a nice thing. First off, in this, can I do this? Can I just pick some arbitrary function which is a superposition of energy eigenstate? Sure, because any function is. Any function can be described as a superposition of energy eigenfunctions. And if I build some if I use energy eigenfunctions, this will automatically satisfy the boundary condition, and all good things will happen. So this is a perfectly fine initial condition. What is the system at time t? Yeah, we just pick up the phases, and what phase is this guy? It's this, e to the minus I, omega n t. And when I write omega n, we need to be more explicit about that, that's en over h bar. So that's h bar kn squared upon 2m t. Cool. So there is our solution for arbitrary initial conditions to the infinite square well problem we want to case.
Mm-hmm. So this is a sum, obviously, because these are discrete values, as we discussed in the last lecture. And then we've got Cn e to the negative and I. I believe, yeah, e to the negative I, h. Because the h cancels. K n squared t divided by 2m. Okay, and that's also because of this one here. I'll just write that down in the front. I missed that one. H n of x is equal to, or so, what was that? H, or psi of xt is equal to x n of x, or psi n of x. Man, reading them out, I'm struggling here. Minus I e n t divided by h bar. I think I did write it down up there. Okay.
You're going to study this in some detail on your problem set. But just to start with a little bit of intuition, let's look at the wave functions and probability distributions for the lowest lying state. So for example, the wave function for the ground state, what I will call psi from 0. And this is from 0 to L. Okay. And I put these bars here not because we're looking at the potential. I'm going to be plotting the real part of the wave function. Well, I put these balls here just to emphasize that that's where the balls are at x equals 0 and x equals 0. So what does it look like? Well, the first one is going to be sine of tan x and 0. Tan is going to be pi upon L. So that's, again, just this guy. Now, what's the probability distribution associated with psi 0? Where do you find the particle? So we know that. It's just the norm squared of this wave function. And the norm squared is here at 0, so it's quadratic. And 0 rises linearly because sine is linear for small values. That means it's quadratic. Maximum and then quadratic. So there's our probability distribution. And here's a funny thing. Imagine I take a particle, classical particle, and I put it in a box. Okay? And you put it in a box and you tell it, okay, it's got some energy, so classically it's got some momentum. So it's sort of bouncing back and forth. It just bounces off arbitrarily hard balls and moves around. Where are you most likely to find that particle? Where does it spend most of its time? It spends the same amount of time at any point. In fact, moving at constant velocity goes, right? So what's the probability distribution for finding it at any point in time classically? Constant. Classically, the probability distribution is constant. You're just as likely to find it near the wall as not near the wall. Okay. However, quantum mechanically, for the lowest lying state, that is clearly not true. You're really unlikely to find it near the wall. What's up with that? So that's a question that I want to put in your head and have you think about. You're going to see a similar effect arising over and over. I'm going to say at the very end that is directly related. The fact that this goes to 0 is directly related, and I'm not kidding, to the transparency of diamond. Now, okay, I think that's pretty cool. Okay, so they're expensive. It's also related to the transparency of zirconium, which I guess is less impressive. But so the first state, again, let's look at the real part of psi 1. The first excited state, well, this is now a sine with 1 extra with a 2 here, 2 pi, so it goes through 0. Okay, so the probability distribution associated with psi 1, I should say, right, this is the function of x, looks like, well, again, it's quadratic, but it has a 0 again in the middle. So it's going to look like, oops, my bad art. Okay, so now it's even worse. Not only is it unlikely to be out here, it's also very unlikely to be found in the middle. In fact, there's 0 probability you'll find it in the middle. That's sort of surprising. But you can quickly guess what happens as you go to very high energies. The real part of psi n, let's say, 10,000, 10 to the 4, what is that going to look like? Well, this had no zeros, this had 1 zeros, and every time you increase n by 1, you're just going to add 1 more 0 to the sign. That's an interesting and suggestive factor. So if it's size of 10,000, how many nodes are there going to be in the middle of the domain? 10,000, and the amplitude is going to be the same. Yeah, I'm not going to be able to do this, but you get the idea. And now if I construct the probability distribution, what's the probability distribution going to be? Probability of the 10,000 psi sub 10 to the 4 of x. Well, it's again going to be strictly positive. And if you are not able to make measurements on the scale of L upon 10,000, let's just say like L over 3, because you have a thumb and you don't have an infinitely accurate meter, what do you see? You see effectively a constant probability distribution. Actually, I shouldn't draw it there, I should draw it through the half. Because sine squared over 2 averages to 1/2. Or sine squared averages to 1/2 over many traits. So what we see is that the classical probability distribution constant does arise when you look at very high energy states. Cool? But it is manifestly not a good description. The classical description is not a good description. Your intuition is crappy at low energies near the ground state, where quantum effects are dominating because indeed classically there was no minimum energy. Quantum effects have to be dominating. And here we see the Leibniz probability distribution is radically different than our intuition. Yeah. Keep working on it. So I want you all to think about what you're not going to, I promise you, unless you've already seen some quantum mechanics, you're not going to be able to answer this question. But I want you to have it as an uncomfortable little piece of sand in the back of your oyster mind. No offense. What is causing that zero? Why are we getting zero? And I'll give you a hint. In quantum mechanics, anytime something interesting happens, it's because of superposition and interference. All right. So, with all that said, so any questions now over this story about energy eigenfunctions, expanding into basis, etc.? Before we get moving? No? Okay. In that case, get out your clickers. You're going to test your knowledge.
Clicker time.
Channel 41, for those of you who have to adjust it. Wow. That's kind of boring. Okay, ready. Okay, channel 41, and here we go. Oops. Okay, so go ahead and start now. Oh, sorry, there was a little few movements there. So, Psi-1 eigenstates.
Okay, Psi1 and Psi2 are two energy eigenstates. The energy operator applied to Psi1 is equal to E1 Psi1. So this is just coming from the idea that they are that they're eigenstates. They are non-degenerate, meaning they have different eigenvalues. Is Psi S, which is Psi1 plus Psi2, also an energy eigenstate? Ooh, well, I know it's not. I know it's definitely not A. It's definitely not the case that it's. No, I'm going to say no, never, because if they have different eigenvalues, they can't both be the same. So I'm going to go with B. Let me just put the timestamp for this so that I know when to come back to this. I want to check it. 24. Click your cues. All right. I'm going to guess B for this one. See what he
They're
says.
non-degenerate, meaning the energies are different. Superposition, Psi1 plus Psi2 also not the same. All right, 4 more seconds. All right, I want everyone to turn to the person next to you and discuss this. You got about 30 seconds to discuss for a minute. All right, I want everyone, now that you've got the answer, click again. Put in your current best guess. Oh, wait, sorry, for some reason I have to start over again. Okay, now, click. This is the best. I'm such a convert to clickers. This is just fantastic. So you guys went from, okay, so roughly y'all went from about 30, 60, 10 to, what are we now? 8, 8 and 82 and 10. So it sounds like you guys are predicting answer B, and the answer is, I like the suspense. There we go. B, good.
B.
So here's a quick question.
Right.
So does anyone want to defend, so why? And the reason why is that if we have E on Psi1 plus Psi2, this is equal to E on Psi1, operator. This is equal to E1 Psi1 plus E2 Psi2, which is not, if E1 and E2 are not equal, which is not equal to E times Psi1 plus Psi2, right? Not equal to E anything times Psi1 plus Psi2. And it needs to be in order to be an eigenfunction of the energy operator. So, yeah. Yeah, okay, that's a really good question. So, first off, how do you measure an energy? Do you ever measure an energy? Like, do you ever measure voltage? The actual value of the scalar potential? Do you measure A? No, you measure A? Difference. Do you ever measure the energy? No, you measure difference in energy. So, the actual value of energy is really thick. But we always talk about it as if it's not, because energy 14. It's a little bit suspicious. So, to answer your question, there's nothing hallowed about the number 0, although we will often refer to zero energy in a very specific meaning. What we really mean in that case is the value of the potential energy infinity. Okay, so when I say like energy usually means relative to the value of infinity. So then you ask your question again. The question is it possible to have energy 0? Absolutely, we'll see that. And it's actually really interesting what's true state of energy 0 in that sense. Second part of your question though is, how does energy being 0 fit into this? Well, does that say, suppose one of the energies is 0. then that says that E on 7 plus psi 2 is equal to E2 is 0. Well, that turns out to just throwing water in energetic state. No, because it's still not 4 E times 7 plus 2. So it doesn't save us, but it's an interesting question for the future. All right. Next question, 4 parts.
Okay, so this is commutator notation. So the commutator of x and p is equal to IH is commutator of px IH is IP plus CX equal to CX IP. Okay, so let's just work this out right here. This is going to be equal to px minus xp. And we know that the answer to xp minus px is equal to IH. So this would be equal to, should it not be negative IH? No, I think it should be negative IH. So I'm going to guess no for the first one. And then the second question is IP plus CX equal to CX plus IP. And in this case, I'm going to say yes, because these are both linear operators. So it's going to go with C, no, and yes. That's my final answer.
So the question says, x and p make I equal. Are you sure this? Is px equal to I bar, and is IP plus CX the same as CX plus IP? Okay. If you're really unsure, you can ask the person next to you, but you don't have to. Okay, so this is looking good. Did everyone have an answer? No? Okay, 5, 4, 3, 2, 1. Okay, good. The answer is C, which most of you got, not everyone. Most of you put B, so let's talk through it. So if x, so remember what the definition of the commutator is. X with p, by definition, is equal to xp minus px. If we change the order here, px is equal to minus this, px minus xp. Okay, this is the definition of the commutator. So on the other hand, if you add things, does 7 plus 6 equals 6 plus 7? Yeah. Well, for 6 times 7 is 7 times 6. That's not going to be the analogy. 2 operators, does the order of addition of operators matter? No. So, yeah. Yeah, exactly. So, okay, next question. Okay, this one has 5. Okay, F and G are both.
Okay, number 3. F and gx are wave functions. I'll shift this up a bit. Fx and gx are wave functions, and c is a constant. Then c times f is g is equal to. Okay, so this notation, cf g, should be equal to dx CFG. So is that not right? Or am I forgetting a complex conjugate here? I forgot whether it was a complex conjugate. Okay, I'm not going to look back at the notes. I'm going to try to answer it without it. So then CFG equals, is it C star? Yeah, it depends on whether there's a, so I'm going to have to look, I guess, because I don't remember. You know what, I'm going to make a guess, and then I'm going to make a guess looking at my notes. So my guess is going to be that, I think there was a complex conjugate. If there's a complex conjugate, then it's B. And let's just sort of just look real quick to see if there was a complex conjugate in this notation. Yeah. Yeah. We talked about this. Where did we talk about it? Here, yeah. Yeah, it's complex conjugate. So that's actually, that should be B.
C is a constant, then if you take the inner product, C times F with G, this is equal to what? Three, two, one. Okay. So the answer is, so this one is definitely discussed. Discuss with the person next to you. right. And okay, go ahead and enter your guess again, or your answer again. Let it not get guess. Okay, 10 seconds. Wow. Okay, fantastic. That was like a chance. So what's the answer? Yes, complex conjugation.
Yeah. Okay. Yeah. All right. Gotta watch those complex conjugates, right? All right.
But don't screw that one up. It's very easy to cut. It matters a lot. Okay. Okay, next one.
Okay. A wave function of psi x has been expressed as the sum of energy eigenfunctions u and x's. All right. Compared to the original psi x, the set of the numbers C1, 2, 3 contains more information, less information, the same information. That would C.
The wave function, right? A wave function is expressed as sum of energy eigenfunctions. Here it's on the u rather than.
Sorry, the set of C's. So not C and U, just C's. Ooh, actually, this is more difficult than I thought. Because the energy eigenfunctions, I think we're missing phase information here, no? Do I want to change my answer? I'm gonna change my answer to B because I think we're missing phase information.
It's 5, but same thing. Compared to the original wave function, the set of coefficients, given that we're using the energy basis, the set of coefficients contains more or less the same information, or it can be determined. Okay, 5 seconds. All right, and the answer is C. Great.
Oh, okay. All right. All right.
Okay, next one.
All energy eigenstates, stationary states, have the form psi equals psi x e to the negative omega t, so that psi, the norm squared of psi xt is equal to the psi of norm squared of psi x is time independent. Consider the sum of two non-degenerate stationary states. Psi sum xt is equal to psi 1 plus psi 2, which is equal to psi 1x times e to the negative I omega 1t plus psi 2e, psi 2x times e to the negative omega 2x. Is this wave function stationary? That is the sum of this independent, time independent? So my guess is that this is not time independent. But does it depend on the, I'm going to say C, because if these are degenerate, like if W, so non-degenerate stationary states, then I'm going to say no, it is not. Sorry, this is not degenerate, so B is going to be my answer.
So right now we're normalizing. Okay, all stationary states or all energy eigenstates have the form spatial time dependence, spatial dependence, the energy eigenfunction, time to phase, so that the norm square is time dependent. Consider the sum of two non-degenerate energy eigenstates. Psi 1 psi 2. Non-degenerates are not energy, they have energy. Is the wave function station? Is the probability distribution time independent or is it time dependent? This one's not true. Oh, shoot, I got to get started. Sorry. Especially when you can't get your answer. Right, so go ahead and enter your answer. Yeah, this one always kills people. No challenges yet. Test yourself, not your neighbor. Yeah, it's fine to look even at yourself. Don't even insult the person sitting next to you. All right. So at this point, chat with your neighbor. Okay. Let me take this impression. The paralyzed strategy is probably not so good because about half of you are right, about half of you are wrong. So.
Ooh, maybe it's C. Because I'm going for kind of an obvious answer here. Maybe there's some omega i's that can, even though they're not degenerate. I'll leave it right here. See what he says.
All right, let's vote again. And hold on, starting now. Okay, vote again. We've got 10 seconds to enter a vote. Wow. Okay, 2 seconds. Good. So the distribution on this one went from 30, 50, 20, initially, to now it is 10, 80, and 10. Amazingly, you guys got worse. The answer is C.
Shoot.
And I want you to discuss with each other why it's C.
I guess because, yeah, I don't know.
All right. So let me tell you the trick. So the wave function we said sine x and t is equal to phi 1 at x e to the minus I omega 1 t m plus phi 2 of x e to the minus I omega 2 t. Right? So great, we take the norm squared. What's the probability to find out x at time t? Probability density is the norm squared of this guy, psi squared, which is equal to phi 1 complex conjugate e to the plus I omega 1 t plus phi 2 complex conjugate e to the plus I omega 2 t times the thing itself, phi 1 of x e to the minus I omega 1 t plus phi 2 of x e to the minus I omega 2 t. Right? And so this has four terms. The first term is psi 1 norm squared. The phases cancel. Right? You're going to see this happen a billion times in 804. The first term is going to be phi 1 norm squared. There's another term which is phi 2 norm squared. Again, the phases exactly cancel. You minus I omega 2 t, the plus I omega 2 t, plus phi 2 squared. But then there are two cross terms, the interference terms, plus phi 1 complex conjugate phi 2 e to the I omega 1 t, the plus I omega 1 t, I omega 1 t, and e to the minus I omega 2 t, minus omega 2. So we have a cross term which depends on the difference in frequencies. Frequencies are like energies modulo h squared, so it's the difference in energies. And then there's another term, which is the complex conjugate of this guy, phi 2 star times phi 1. Phi 2 complex conjugate, phi 1, and the phases are also the complex conjugate, e to the minus I omega 1 minus omega 2 t of x, of x, of x, of x. So is there time dependence in this in principle? Yeah, absolutely. From the interference terms. Were we not in a superposition, we would not have the interference terms. Time dependence comes from interference when we expand in energy functions. Cool? However, can these vanish? When? Sorry, say again? Great. So when omega 1 equals omega 2, what happens? Time dependence goes away, but omega 1 is E1 over H bar. Omega 2 is E2 over H bar. We started out by saying these are non-degenerate. So if they're non-degenerate, the energies are different, the frequencies are different. But that doesn't help us. How do we kill this time dependence? Yes, if the two functions are just orthogonal in a functional sense, but if we have the following, suppose phi 1 is like this, it's 0 everywhere except for in some 1, that's phi 1, and phi 2 is 0 everywhere except here. Then anywhere phi 1 is non-zero, phi 2 is 0, and anywhere phi 2 is non-zero, phi 1 is 0. So this can pointwise vanish. Do you expect this to happen generically? Does it happen for the energy eigenfunctions in the infinite square well? Sine waves? No, some they have 0 at isolated points, right? They're non-zero generically. Yeah, so it doesn't work there. What about for the free particle? Well, those are just plane waves. Does that ever happen? No. Okay, so this is an incredibly special case. We'll actually see it in one problem on our problem set later on. It's a very special case. So technically the answer is C. And I want you guys to keep your minds open on these sorts of questions. When does the spatial dependence matter? And when are there interference terms? Those are two different questions. I want you to tease them apart. Okay? Cool? Yeah.
Well, I got that one wrong, but looks like most of the MIT students did too. We done click questions, or are there more click questions?
Overall thing. So that's a very, very good question. So the question, let me say that slightly differently. Let me disagree with what you're just saying. So look, I can look at this wave function, and I already know that the overall phase of a wave function doesn't matter. That's what it is to say stationary state is stationary. It's got an overall phase. That's the only thing that, in order to where it goes away. So I can write this as the minus I omega 1 t times phi 1 of x plus phi 2 of x e to the minus I omega 2 minus omega 1 t. Is that what we need? So that's one way to do this. We also do something we do e to the minus I omega 1 plus omega 2 on 2t. This is more I think what you're thinking of, sort of average frequency and a relative frequency. And then the change in frequency on these two terms. Absolutely. So you can organize this in many, many ways. But the important thing is, your question is a very important point. So the overall phase doesn't matter. But relative phases in superposition do matter. So when does a phase matter in a wave function? It doesn't matter if it's an overall phase, but it does matter if the relative phase between terms in superposition. Cool? Very good question. Other questions? If not, then I have some. So, consider a system which is in a state. Oh, so I should give you 5. System is in a state.
Oh, we got more questions. All right. Question number, I'll just put it over here. 6. System is in a state which is a linear combination of the n equals 1 and n equals 2 energy eigenstates. All right. What is the probability of the measurement of what is the probability that a measurement of energy will yield energy E1? Where's the E1? Oh, I guess it just corresponds to this psi one. What is the probability that measurement of the energy Well, I think we just have to do the norm squared, right? Like, I want to say this is 1/2 because when we do norm squared, this is going to be like the I and the +1 are orthogonal, right? Just eyeballing it, maybe. C is my eyeball guess, so let's see if it changes when I actually do the math. So P is going to be equal to this squared, or the complex conjugate of this, which we're going to take. So this is I over 2 e to the negative I 1t psi 1 x plus 1/2 1/2 e to the negative psi 2 x, and then we're going to multiply these together, but we're going to have to multiply this one by I first. And then this one is going to be I to the negative for this right here. Oops, I'm dropping I's. Dropping my I's. Dropping my I's, guys. So we're going to have these two multiply out, and this probability density is going to be equal to, this is going to be, so this, let's see, this is going to be I times, this is going to be real, and this is going to be, real, and this is a little bit of a mess right here. I don't know what's the best way to figure this out. Oh, I'm eyeballing it. I'm saying 1/2, but I'm going to have to work on some methods for solving these a little better because this is obviously taking too long for a quicker question. So when we multiply these are going to be imaginary. I'm just going to put in the, just going to put in C for right now and see whether I was at least right on the estimate.
Which is a linear combination of n = 1 and n = 2 eigenstates. What's the probability that the measurement will give us energy E1? And it's in this superposition. Okay, 5 seconds.
Yeah, it's got to be 1.
Fantastic. What's the answer? Yes, C. Great. Okay, I forgot that one. So this one's a slightly, this one's a more interesting question. Suppose I have an infinite well with width L.
How does the energy, so this one here, I'm not sure why, I've got to think about that a little bit more, why I'm not able to just grok that, obviously, but I do see it's 1/2, but I got the right answer, but I don't feel that confident in how I was supposed to do that calculation really quickly. All right, how does the energy E0 of the ground state of an infinite well with L compare with the energy of the ground state of a well with a larger width? The wider well has lower energy, higher energy, same energy, need more information. Well, I'm going to say it's going to be higher energy because you're having a more, you need to have shorter wavelength.
How does the energy, the ground state energy, compare to that of a system with a wider well?
gotta be B, right? Oh, a wider well has lower energy. Sorry, I'm reading that wrong. Wider well has lower energy because it's a longer wavelength.
So L versus a larger L. Okay, 4 seconds. Okay, quickly discuss amongst yourselves. What 10 seconds? All right. Now think again. Yeah. All right, 5 seconds. 1, 2, 3, 4, 5. Great. Okay, the answer is A. Okay, great. You do because the energy of the infinite well goes like K squared. K goes like 1 over L. Okay, so the energy is if you make it wider. The energy if you make it wider is going to be lower. And last couple of questions. Okay, so.
All right, let's try this one. 8. At t equals 0, could the wave function for an electron in the infinite square well of width A, okay, be psi x at time 0, A sine squared, where A is a suitable normalization constant. At t equals 0, could the wave function for an electron in infinite be this? So if we have some well, and this is saying sine squared, which is like a, how do I draw sine squared? It's like it's more like this, I think. I think that's what sine squared looks like. Sure, no, it's not physical. So I guess the question is, can you construct sine squared out of energy eigenstates? I'm gonna say A. I'm gonna say A. Yeah, you can make this. That's my theory, at least. Let's see why I'm wrong.
The wave function for an electron in an infinite square well of width A, rather than L, the A sine squared of pi x upon A, where A is just to be normalized.
Bracing myself on this one. I think it's C. I think it's A, because this meets the boundary conditions, no?
All right.
And you can create it out of.
And okay, we are at chance. We're at eons, and the answer is not a superposition of A and B. So I encourage you to discuss with people. Right, what properties that are satisfied in order to be a viable wave function? What properties should the wave function have so that it's feasible? Yeah, is it 0 the answer? Is it smooth? Yeah. Exactly. I see you as a superposition. So the answer is yeah. All right. Vote again. Okay, go ahead. One more message you can. Go ahead, sorry. Yeah. Okay, 5 more seconds. All right. So we went from 50-50 to 77-23. That's pretty good. What's the answer? Hey, why?
Oh, okay, good.
Is this an energy eigenstate? Does that matter? No. What properties have this wave function better satisfied to be a reasonable wave function in this potential? Second, it's not advantage to the walls, that's satisfied the boundary condition. What else must be true in this wave function? Normalizable. Is it normalizable? Yeah. What else? Continuous. Is better not having this is it continuous? Is there any reason that this is a stupid wave function? No, it's perfectly reasonable. It's not, an energy function, but yeah, cool. Yeah. On this domain, these are that and some are even. Right. So this is actually one we're looking at from 0 to L. Right. So I mean that half of it. The signs are odd, but we're looking at the first B. So if you just well written that as cosine of the midpoint plus the distance from the midpoint. Cool. This actually, let me say that again because it's a much better question than I just gave a trick for. So here's the question. The question is, look, this function in this, so sine is an odd function, but sine squared is an even function. So how can you expand sine squared and an even function in terms of sine is an odd function? But this is, think about this physically. Here's sine squared in our domain, and here's sine. Now, what do you mean by even? Usually by even we mean reflection around 0. But I could just as well have said reflector around the origin. This potential is symmetric. And the energy eigenfunctions are symmetric about the origin. They're not symmetric about reflection around this point, but they are symmetric about reflection around this point. That's usually an action place called 0. So I was calling them sine, so I was calling this 0. But I could have called cosine if I called this 0. Cool. For the same kx. Okay. And indeed, can we expand this sine squared function in terms of a basis of these sines on the domain 0 to L? Absolutely. Very good question. Okay, and lastly, last clicker question. Oops.
All right, here we go.
Okay.
All right, at t equals 0, the wave function for a particle in an infinite well of width a is this psi x 0 equals a sine squared x, where a is a suitable normalization constant. Which of the following is true about the wave function psi xt at time t? So which is time independent when we know that's not true. It's not a. Psi xt a sine squared s is where E is the energy of the electron. E is the nth stationary state. Can't quite see what's there. E is the nth stationary state. D, well, it's got to be D because it's the only one that's a sum of these. So is a sum of these things where C is equal to, I'm going to guess D. I'm not going to work out this calculation, but that's the only one that seems plausible to me.
Zero. The particle is described by the wave function we just saw. Which is true of the following, which the following is true about the wave function at subsequent times. Five seconds. Oh, okay. In the last few seconds, we have explicit burst for A and C. So our current distribution is 8, 16, 10, and 67. Sounds like 67 is popular. Fast quickly. Very quickly. The first next to you. Okay. And vote again. Okay, 5 seconds. Get your last vote in. All right. And the answer is D.
Okay. Yeah.
Okay.
Good.
And the reason is, so let's think about the logic. Let's go through the logic here. So as was pointed out by student, the wave function sine squared of Ix can be expanded in terms of the energy. Any reasonable function can be expanded in terms of superposition of definite energy states of energy functions. So then you can write side at some time as a superposition Cn sine of A equals E and T each part. This is already B. So here, each term in that superposition evolves with a phase. The overall wave function does not evolve with a phase. It is not an energy state. There are going to be interference terms due to the fact that it's a superposition. So probability distribution is not it is a superposition, so the wave function doesn't work by the phase. However, we can solve the Schrödinger equation as we did before. The wave function is expanded at time 0 as the energy function times the coefficients, and the parallel relation corresponds to adding to each independent term in this superposition the appropriate phase for that energy state. Cool. All right, so the answer is D. And that's it for the clicker questions. Okay, so any questions on the clicker questions so far? Okay, those are going to be closed on so you can go over them. And now back to energy functions. Okay. So what I want to talk about now is the qualitative behavior of energy functions. Suppose I now have an energy function. What can I say generally about
stool here.
So let me ask the question for qualitative behavior. So suppose someone hands you a potential U of X. Someone hands you some potential U of X and says, look, I've got this potential, and maybe I'll draw it for you. It's got some wiggles, and then a big wiggle, and then it's got a big wiggle, and then, do you want to do that? Yeah, let's do that. And a big wiggle, and something like this. And someone shows you this potential, and they say, look, what are the energy eigenfunctions? Okay. Well, okay, free particle was easy. The infinite square well is easy. We could solve that analytically. But that's involves solving a differential equation. So what differential equation is that going to lead us to? Well, we know that the energy eigenvalue equation is minus h bar squared upon 2m phi prime prime of x plus u of x, 5x. So that's the energy operator acting on phi is equal to, saying that it's an energy eigenvalue, says that, that it's an energy eigenfunction, phi sub e, says that it's equal to the energy operator acting on this eigenfunction. It's just a constant e, phi sub e of x. I'm going to work at a moment in time, so we're going to drop all the t dependence for the moment. So this is the differential equation we need to solve, where u of x is this god-awful function. Right? Do you think it's very likely that you're going to be able to solve this analytically? Yeah, probably not. However, some basic ideas will help you get an intuition for what the wave function should look like. And this is, I cannot overstate the importance of being able to eyeball a system and guess the qualitative features of its wave functions, because that intuition, that ability to estimate, is going to contain an awful lot of physics. So let's try to extract it. So in order to do so, I want to start by massaging this equation into a form which is particularly convenient. So I'm going to write this equation as phi sub e prime prime. So what I'm going to do is I'm going to take this term. I'm going to notice this is two derivatives, this has no derivatives, this has no derivatives. And I'm going to move this term over here and combine these terms into e minus u of x. And I'm going to divide each side by 2m upon h bar squared with the minus sign, giving me that phi prime prime of e of x upon phi e of x, dividing through by this phi e, is equal to minus 2m over a squared. And let's just get our sign right. We've got the minus from here, so this is going to be e minus u of x. Okay. So you might look at that and think, well, why is that any better than what I just written down? But what is the second derivative of a function?
Acceleration.
It's telling you how the slope changes. Right? It's telling you about the curvature of the function. And what this is telling me is something very, very useful. If I know, so for example, let's look at the function. Let's assume that the function is real, although we know in general it's not. Let's assume that the function is real for simplicity. So we're going to plot the real part of phi. Okay, the vertical axis, and this is x. Suppose the real part of phi is positive. Okay, at some point. Phi prime prime, if it's positive, tells us that not only is the slope positive, it's increasing. Or it doesn't tell us anything about the slope, it tells us whatever the slope, it's increasing. If it's negative, the slope is increasing as we increase x. If it's positive, it's increasing as we increase x. So it's telling us that the wave function looks like this locally. Yeah, something like that. If phi is negative, okay, if phi is negative, then if this quantity is positive, then phi prime prime has to be negative. But negative is curving down. So if this quantity, which I will call the curvature, if this quantity is positive, it curves away from the axis. So this is phi prime prime over phi greater than 0. If this quantity is positive, the wave function, or the function curves away from the axis. Cool? If this quantity is negative, phi prime prime upon phi less than 0, exactly the opposite. This has to be negative. If phi is positive, then phi prime prime has to be negative. It has to be curving down. Yeah? And similarly, if phi is negative, then phi prime prime has to be positive and it has to curve up. So if this quantity is positive, if the curvature is positive, it curves away from the axis. If the curvature is negative, if this quantity is negative, it curves towards the axis. So what does it tell you about solutions when the curvature is positive or negative? It tells you the following. It tells you that imagine we have a function where phi prime prime over phi is constant. Okay, and in particular, let's let phi prime prime over phi be a constant which is positive, or sorry, let's say positive. And I'll call that positive constant kappa squared. And to emphasize that it's positive, I'm going to call it kappa squared. This is a positive thing, it's a real number squared. Okay, what does the solution look like? Well, this quantity is positive, and it's always going to be curving away. So we have solutions that look like this, or solutions that look like this. Can it never be 0? Yeah, sure, it could be an inflection point. So every time here the curvature is positive, but at this point the curvature has to switch to be like this. What functions are of this form? Let me give you another hint. Here's one. Is this curvature positive? Yes. What about this one? Yeah, those are all positive curvature. And these are exponentials. And the solution to this differential equation is e to the plus kappa x, or e to the minus kappa x. And an arbitrary solution to this equation is a superposition a e to the kappa x plus b e to the minus kappa x. Everyone go with that? When this quantity is positive, we get growing and collapsing exponentials. Yeah? On the other hand, if phi prime prime over phi is a negative number, i.e. minus what I'll call k squared, then the curvature has to be negative. And what functions have everywhere negative curvature? Sinusoidals. Cool? And the general solution is a e to the I kx plus b e to the minus I kx. It's that difference equation. Also known as sine and cosine. Cool? So, putting that together with our original function, so we want to think about the wave functions here. But in order to think about the energy action states, we need to decide on energy. We need to pick an energy. Because you can't find the solution without picking it. But notice something nice here. So suppose the energy is E, and let me just draw E. This is a constant, the energy is this. This is the value here during potential, the value of potential, this is the value of the energy. It's a constant, it's just a number. If you had a classical particle moving in this potential, what would happen? It would roll around, so for example, say you gave it this energy by putting it here, and think of this as a gravitational potential. You put it here, you let go, and it falls down, and it'll keep rolling until it gets up here to the classical turning point. And at that point, its kinetic energy must be 0 because this potential energy is this potential energy. At which point it will turn around and fall back. Yes? If you take the ball and put it here and you let it roll, does it ever get here to this position? No, because it doesn't have enough energy. Right? Classically, this is a forbidden position. So, given an energy and given a potential, we can break the system up into classically allowed zones and classically forbidden zones. Cool? Now, in a classically allowed zone, the energy is greater than the potential. And in a classically forbidden zone, the energy is less than the potential. Remember that? But this tells us something really nice. If the energy is greater than the potential, what do you know about the curvature? Yeah, if we're in a classically allowed zone, so if the energy is greater than the potential, then this quantity is positive. There's a minus up here, so this is negative. So the curvature is negative. Remember, curvature is negative means that we curve towards the axis. So in a classically allowed region, a wave function should be sinusoidal. What about the forbidden regions? In less than the regions, energy less than the potential. That means in magnitude, this is less than this. This is a negative number, minus sign. The curvature is going to be minus sign, so minus is positive. So the curvature is positive. So the solutions are either growing exponentials or shrinking exponentials, or superpositions of them. Remember that? So let's think about a simple example. Let's work through this in a simple example. Let me give you a little bit more board space. Simple example would be a potential that looks like this. Okay, let's just suppose we want to find an energy having a function with energy. It's E. Well, this is a classically allowed zone, and these are the classically forbidden regions. Now I want to ask, what does the wave function look like? And I don't want to draw it on top of the energy diagram because wave function is not an energy. Wave function is different quantities, it's got different axes, and I want to draw them in a different line. So, but as a function of x, so just to get position straight, these are the bounds of the classically allowed and forbidden regions. Okay. What do we expect? Well, we expect that it's going to be sinusoidal in here. We expect that it's going to be exponential, or we're converging up here. X. Right? But one last important thing is that not only is the curvature negative in here, in these classically allowed regions, but the magnitude of the curvature, how rapidly it's turning over, how big that second derivative is, depends on the difference between the energy and the potential. The greater the difference, the more rapid the curvature, the more rapid the turning over and fluctuation. If the difference between the potential and the true energy, the total energy, is small, then the curvature is very small, so the derivative changes very gradually. What does that tell us? That tells us that in here, the wave function is oscillating rapidly because the curvature, the difference between the energy and the potential is large, and so the wave function is oscillating rapidly. As we get out towards the classical turning points, the wave function will be oscillating less rapidly. The slope will be changing more gradually. And as a consequence, two things happen. I actually brought this with you currently. So as a consequence, two things happen. One is the wavelength gets longer, because the curvature is smaller. And the second is the amplitude gets larger, because it keeps on having a positive slope for longer and longer, and it takes longer to curve back down. So here we have rapid oscillations. And then
That's the wrong way to draw that.
Until we get out to the classical turning point. And at this point, what happens? Yeah, it's got to get finished. Now here we have some sign, some superpositions of sine, cosines, exponentials. And if you go to right here with some slope and with some value. We know on this side we've got to get exponentials. And so this sum of sine and cosine at this point must match that sum of exponentials. How must it do so? What must be true of the wave function at this point? Can it be discontinuous? Can its derivative be discontinuous? No, so it's the value and the derivative must be continuous. So that tells us precisely which linear combination of positive growing and shrinking exponentials we get. So we get some linear combination which may do this for a while, but since it's got some contribution of positive exponential, it'll just grow exponentially off infinity. And as the energy gets further and further away from the potential, now in the negative sign, what happens to the rate of growth? It gets more and more rapid, so this just diverges more and more rapidly. Similarly, out here, we have to match the slope. And we know the curvature has to be not positive, so it has to do this. So two questions. First off, is this sketch of the wave function a reasonable sketch, given what we know about curvature and this potential, of a wave function with that energy? Are there ways in which it's a bad estimate? Okay, excellent.
Wait.
Absolutely couldn't cross zero. So I may have drawn this badly and it turned out a little subtle. It's not obvious. Maybe it actually punched all the way through zero and then it diverged down negative. That's absolutely positive. So that was one of the equivalents you could have. Another equivalent you could have is that it looks like I have constant wavelength in here, but the potential is actually changing. And what you should chalk this up to, because part of the fun, is my artistic skills are limited. Okay? So this is always going to be sort of inescapable, that it's when you qualitatively draw something, on a test, I'm not going to value points on things like that. That's what I want to emphasize. But the second thing, is there something bad about this wave function? Yes, you've already named it. What's bad about this wave function? It's badly non-normalizable, right? It diverges off to infinity out here and out here. What does that tell you? It's not physical good. What else does it tell you about this system? Sorry? Excellent. Is this an allowable energy? No. If the wave function has this energy, it is impossible to make it continuous, assuming that I drew it correctly, and have it converge. Is this wave function allowable? No, because it does not satisfy our boundary conditions. Our boundary conditions are that the wave function must vanish out here, and it must vanish out here at infinity in order to be normalizable. Here we failed. Now, you can imagine that, so let's decrease the energy a little bit. If we decrease the energy of our trial energy, just a little tiny bit, what happens? Well, that's going to decrease the curvature in here. If we bring the energy a little tiny bit, that means this is a little bit smaller, the potential stays the same. So the curvature in the allowed region is just a little tiny bit smaller. And meanwhile, the allowed region has got just a little bit thinner.
No, I'm going to draw this differently.
So now we have... Sorry. Get excited. And if we tweak the energy, we can have what's going to arrive here a little bit sooner. And let's imagine something like this. And if we chose the energy just right, we would get it to match to a linear combination of collapsing and growing exponentials, where the contribution from the growing exponential in this direction vanishes. Right? There's precisely one value of the energy that lets me do that with this number of wiggles. And so then it goes through and does its thing. And we need it to happen on both sides. Now, if I take that solution so that it achieves convergence out here, and it achieves convergence out here, and I take that energy and I increase it by epsilon, by just the tiniest little bit, what will happen to this wave function? It will diverge. It will no longer be normalizable. When you have classically forbidden regions, are the allowed energies continuous or discrete? And that answers a question from earlier in the semester, from earlier in the class, and it also is going to be the beginning of the answer to the question, why is the spectrum of hydrogen discrete? See you next time.
Okay. All right. So we did this class here. Trying to think of whether I want to go over the individual points. A lot of this was clicker questions. So let me just go remind myself what we covered other than this, which this is kind of like the sort of non-infinite well case, showing that we have these boundary conditions that basically we need outside for them to decay to exponentials. And if they're leaving that zone, the curvature is going to not make it work for non-discrete values. What else did we cover in this lecture? Yeah, more stuff on the excited wells. A lot of it was clicker questions. I'm trying to think if there's any other things that were covered here. Just this notation, some stuff from the last class. So it's mostly this kind of intuitive picture of bound states that we're looking at here. And I want to maybe just draw one more just so that I can get kind of a better idea for it. No, see, I'm drawing it wrong. Okay, let's draw this is our potential, so that you can imagine this is some kind of soft rolling hill, and this is going to be our energy state. And if this is the energy state, then if this was a ball and you rolled it down here, it wouldn't go past here. And this is where it would stay. But in a quantum mechanical sense, what we've got is we've got the curvature of psi in classical is going to be like this, okay, in allowed zone, which as we can see is like a sine wave, and in disallowed, or sort of greater than potential, so energy is it less than potential? What am I looking at here? Yeah, energy is less than the potential. In this case, we have these are solutions to this. And the distance from E is equal to curvature strength for allowed. That's going to be equal to frequency. So because this is deeper here, we've got a little bit more ripples, and then they get more spread out. And once they get more spread out, once we get out of this region, if we are outside when we are in this region, so this is right here. If we're aiming, if we're above, we're going like this. No, that's not right. Yeah, so we have to basically do it so that the downward force of this and the upward force of this exactly match out, so we hit this. So this is sort of like it's accelerating downwards and accelerating upwards. So this is to smooth out just to hit the asymptote of 0. If it goes, if it's not matched, so if this doesn't exactly match this, it's going to go out of control, because it's either going to be if it doesn't go if it doesn't go below the it's going to go either like this or like this, and it's going to go off to infinity in some direction. I think that makes sense. So mostly clicker questions. I felt pretty good about the clicker questions. I got one thing wrong on the phase there, because I thought phasal information was in the thing as opposed to the coefficients, but maybe I'm wrong. All right, let's go forward with an hour left. Let's see if we can get done lecture 8.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Today,
We got Barton again.
we begin with the harmonic oscillator. And before getting to the harmonic oscillator, I want to touch on a few concepts that have been mentioned.
Don't worry, I'll be putting my notes up at the end of the project, I think.
Nodes and how solutions look at, and why solutions have more and more nodes, why the ground state has no nodes, this kind of stuff. So, so these are just a collection of remarks and an argument for you to understand a little more intuitively why these properties hold. So, one first thing I want to mention is if you have a Schrödinger equation for an energy eigenstate, Schrödinger equation for an energy eigenstate, you have an equation of the form minus h squared over 2m d second dx squared psi of x plus v of x psi of x equal e times psi of x. Now, the issue with this equation is that you're trying to solve for two things at the same time. If you're looking at what we call bound states, now what is a bound state? A bound state is something that is not extended all that much. So a bound state will be a wave function that goes to 0 as the absolute value of x goes to infinity. So it's a probability function that certainly doesn't extend all the way to infinity. It just collapses, it's normalizable. So these are bound states, and you're looking for bound states of this equation, and your difficulty is that you don't know psi and you don't know e either. So you have to solve a problem in which, if you were thinking, oh, this is just a plain differential equation, give me the value of e, we know the potential, just calculate it. That's not the way it works in quantum mechanics, because you need to have normalizable solutions. So at the end of the day, as will be very clear today, this e gets fixed. You cannot get arbitrary values of e's. So I want to make a couple of remarks about this equation, is that there's this thing that can't happen. If v of x, certainly if v of x is a smooth potential, then if you observe that the wave function vanishes at some point and the derivative of the wave function vanishes at that same point, these two things imply that psi of x is identically 0. And therefore, it means that you really are not interested in that. That's not the solution of the Schrödinger equation. Psi equals 0 is obviously solves this. That's not interesting. It doesn't represent the particle. So what I claim here is that if it happens to be that you're solving the Schrödinger problem with some potential, it is smooth, you get the derivatives of it, and then you encounter that the wave function vanishes at some point and its slope vanishes at that same point, then the wave function vanishes completely. So you cannot have a wave function at psi of x that does the following. It comes down here and it becomes an inflection point and goes down. This is not allowed. If the wave function vanishes at some point, then the wave function is going to do this. It's going to hit at an angle, because you cannot have that the wave function is 0 and its derivative 0 at the same point. And the reason is simple. I'm not going to prove it now here. It is that you have a second-order differential equation, and a second-order differential equation is completely determined by knowing the function at the point and the derivative at the point. And if both are 0, it's like the most trivial kind of initial condition. The only solution consistent with this is psi equals 0 everywhere. So this can't happen. And it's something good for you to remember. If you have to do a plot of a wave function, you should never have this. So this is what we call the node in a wave function. It's a place where the wave function vanishes, and the derivative of the wave function better not vanish at that point. Now, there's another, so this is one claim that it's not hard to prove, but we just don't try to do it. And there's another claim that I want you to be aware of, that for bound states, in one dimension, in the kind of thing that we're doing now in one dimension, no degeneracy is possible. What do I mean by that? You will never find two bound states of a potential that are different and have the same energy. It's just absolutely impossible. It's a very wonderful result, But also, I'm not going to prove it here. Maybe it will be given as an exercise later in the course, and it's discussed in 805 as well. But that's another statement that is very important. There's no degeneracy. Now, you've looked at this simple potential, the square well, infinite one. And how does it look? You have x going from 0 to a, and the potential is 0. From 0 to a is infinite otherwise, and the particle is bound to stay inside the two walls of this potential. So here we've plotted the potential as a function of x. Here's x. And the wave functions are things that you know already. Yes?
Is it true if you have two wells next to each other that there's no degeneracy?
If there's two wells and there's an infinite barrier between them, it's like having two universes. So it's not really a one-dimensional problem. If you have an infinite barrier, it's like two worlds that can't talk to each other. So yes, then they would have degeneracy. It's like saying you can have here one atom of hydrogen or something in one energy level, here another one. They don't talk to each other. They're degenerate states. But in general, we're talking about normal potentials that are preferably smooth. Most of these things are true, even if they're not smooth, but it's a little more delicate. But certainly, two potentials that are separated by an infinite barrier is not part of what we really want to consider. Okay, so these wave functions start with n equals 0, 1, 2, 3, and sine n's of x are square root of 2 over a sine n plus 1 pi x over a. Things that you've seen already. And ENs, the energies, are ever growing as a function of the integer n that characterizes them, 2mh squared. And the thing that you notice is that the psi 0 has technically no nodes. That is to say, these wave functions have to vanish at the end because the potential becomes infinite, which means the particle really can't go through. The wave function has to be continuous. There cannot be any wave function to the left, so it has to vanish here. These things don't count as nodes. It is like a bound state has to vanish at infinity, and that's not what we count a node. The node is somewhere in the middle of the range of x where the wave function vanishes. So this is the ground state. This is psi 0, has no nodes. Psi 1 would be something like that, has one node. And try the next ones, they have more and more nodes, so psi n has n nodes. And the interesting thing is that this result actually is true for extremely general potentials. You don't have to just do the square well to see that the ground state has no nodes, the first excited state with one node, and so on and so forth. It's true in general. Now, this is actually a very nice result, but it's difficult to prove. In fact, it's pretty hard to prove. And so there's a nice argument, not 100% rigorous, but fairly nice and really physical, that I'm going to present to you why this result is true. So let's try to do that. So here's the general case. I'm going to take a smooth v of x that will be of this kind. The potential here is x, and this potential is going to be like that. Smooth all over, and I will actually have it that it actually goes to infinity as x goes to infinity. Many of these things are really not necessary, but it simplifies our life. Okay, so here is a result that is known to be true. If this thing grows to infinity, the potential never stops growing. You get infinite number of bound states at fixed energies, 1 energy, 2 energy, 3 energy, infinite number of bound states. Number of bound states. That's a fact. I will not try to prove it. We'll do it for the harmonic oscillator. We'll see those infinite number of states. But here, we can't prove it easily. Nevertheless, what I want to argue for you is that these states, as the first one, will have no nodes. The second state, the first excited state, will have one node. The next will have 2 nodes, 3 nodes, 4 nodes. We want to understand what is this issue of the nodes. Okay, so you're not trying to prove everything, but we're trying to prove or understand something that is very important. So how do we prove this? Or how do we understand that the nodes, so there will be infinite number of bound states, psi 0, psi 1, psi 2, up to psi n, and it goes on, and psi n has n nodes. All right. So what I'm going to do, in order to understand this, is I'm going to produce what we will call screened potentials. Screened potentials. I'm going to select the lowest point of the potential here for convenience, and I'm going to call it x equals 0. Is the lowest point. And the screen potential, it will have a parameter a, is a potential which is equal to v of x if the absolute value of x is less than a, and it's infinity if the absolute value of x is greater than a. So I come here and I want to see, this is this potential, v of x. What is the screen potential for some a? Well, I want that color chalk, but I don't have it. I go mark a here, minus a. Here are the points between x and a. X, absolute value of x less than a. Throughout this region, the screen potential is the potential that you have. Nevertheless, for the rest, it's infinite. So the screen potential is this thing. It's infinite there, and it's here, this thing. So it's just some potential. You take it like a screen, and you just see one part of the potential, and then it goes to infinity. So that's a screen potential. So now what I'm going to do is I'm going to try to argue that you could try to find the bound states of the screen potential, and as you remove the screen, you will find, as you let a goes to infinity, you will find the bound states of your original potential. It's reasonable that that's true, because as you remove the screen, you're letting more of the potential be exposed and more of the potential be exposed, and the wave functions eventually die. So at the time that you're very far away, you affect the wave functions less and less. So that's the argument. We're going to try to argue that we're going to look at the bound states of the screen potentials and see what happens, what do they tell us about the bound state of the original potential. So for this, I'm going to begin with a screen potential in which a goes to 0 and say that a is equal to epsilon, very small. So what potential do I have? A very tiny potential here from epsilon to minus epsilon. Now I chose the original point down here to be the minimum. So this actually, the bottom part of the potential is really flat. And if you take epsilon going to 0, well, the potential might do this, but really at the bottom for sufficiently small epsilon, this is an infinite square well with size 2 epsilon. You know, I chose the minimum so that you don't get something like this. If it would be a point with a slope, this would be an ugly thing. So let's choose the minimum, and we have the screen potential here, and that's it. Now look what we do. We say, all right, here there is a ground state, very tiny, looks like that, vanishes here, vanishes there, and has no nodes, very tiny, you know, the two zeros are very close to each other. And now I'm going to try to increase the value of the screen, a. So suppose we've increased the screen, and now the potential is here, and now we have a finite screen. Here's the potential, and I look at the wave function, how it looks. Here's psi 0, this ground state 1, psi 0. Well, since this thing in here, the potential becomes infinite, the wave function still must vanish here and still must vanish here. Now, just for your imagination, think of this, at this stage, it still more or less looks like this. Maybe. Now, I'm going to ask, as I increase, can I produce a node? And look what's going to happen. So suppose it might happen that as you increase, suddenly you produce a node. So here's what I'm saying here. I'm going to show it here. Suppose up to this point, there is no node, but then when I double it, when I increase it to twice the size, when I go to screen potential like that, suddenly there is a node in the middle. So if there is a node in the middle, one thing that could have happened is that you have this. And now look what must have happened then. As I stretch this slope must have been going down and down and down until it flips to the other side to produce a node here. It could have happened on this side, but it's the same. So the argument is just done with this side. To produce a node, it could have done somehow, the slope here must have changed sign. But for that to happen continuously, at some point, the slope must have been 0. But you cannot have a 0 on 0 slope. So this thing can't flip, can't do this. Another thing that could have happened is that when we are here already, maybe the wave function looks like that. It doesn't flip at the edges, but produces something like that. But the only way this can happen continuously, and this potential is changing continuously, is for this thing, at some intermediate stage, as you keep stretching the screen, this sort of starts to produce a depression here, and at some point to get here, it has to do this. But it can't do this either. It cannot vanish and have a derivative like that. So actually, as you stretch the screen, there's no way to produce a node. That property forbids it. So by the time you go and take the screen to infinity, this wave function has no nodes. Okay, so that proves it that the ground state has no node. You could call this a physicist proof, which means, not in a pejorative way, it means that it's.
All right, I'm not able to follow all of his pictures, so I'm just going to write down some of the high-level notes here. So if we take a ground state, the square well, and stretch it out continuously, we can't get a node because otherwise psi equals psi this equals 0 at some point. Okay.
Reasonable, it's intuitive, and a mathematician working hard to make it rigorous. A bad physics proof is one that is a little sloppy and no mathematician can fix it and make it work. So I think this is a good physics proof in that sense. You can construct a real proof or based on this, a very precise proof. Now look at excited states. Suppose you take now, here, the screen very little, and now consider the third excited state, psi 3. This is, I'm sorry, we'll call it psi 2 because it has 2 nodes. Now, well, maybe I should do psi 1. Let's go, so, psi 1, 1 node. Same thing, as you increase it, there's no way to create another node continuously because again, you have to flip at the edges or you have to depress in the middle. So this one will evolve to a wave function that will have 1 node in the whole big potential. Now, does that state have more energy than the ground state? It certainly begins with a small screen with more energy because in the square well, psi 1 has more energy. And that energy should be clear that it's not going to go below the energy of the ground state. Why? Because if it went below the energy of the ground state slowly, at some point, for some value of the screen, it would have the same energy as the ground state. But no degeneracy is possible in one-dimensional problems. So that can't happen, cannot have that. So it will always stay a little higher. And therefore, with 1 node, you will be a little higher energy. With 2 nodes, it will be higher and higher. And that's it. That's the argument. We've argued by this continuous deformation process that this potential not only has these bound states, but this is n nodes, and En is greater than En prime for n greater than n prime. So the more nodes, the more energy. Pretty nice result, and that's really all I wanted to say about these problems. Are there any questions? Any? Okay. So what we do now is the harmonic oscillator. That's going to keep us busy for the rest of today's lecture. It's a very interesting problem, and it's a most famous quantum mechanics problem, in a sense, because it's happens to be useful in many, many applications. If you have any potential, so what is the characteristic of the harmonic oscillator? Harmonic oscillator. Well, the energy operator is p squared over 2m, plus we write 1/2 m omega squared x squared, where omega is this omega that you always think of angular velocity or angular frequency. It's more like angular frequency. Omega has units of 1 over time. Is actually 2 pi over the period of an oscillation. And this you know from classical mechanics. If you have a harmonic oscillator of this form, yeah, it actually oscillates with this frequency. And E is the energy operator. This is the energy of the oscillator. So what defines an oscillator is something in which the potential energy, this term, is V of x. V of x is quadratic in x. That is a harmonic oscillator. Then you arrange the constants to make sense. This has units of energy because this has units of length squared, 1 over time squared. Length over time is like velocity squared times mass is kinetic energy. So this term has the units of energy. And you're good with that. And why is this useful? Because actually, any sort of arbitrary potential, rather general potential at least, whenever you have a minimum where the derivative vanishes, then the second derivative need not vanish, and then it's a good approximation to think of the potential at the minimum as a quadratic potential. It fits the potential nicely over a good region, and therefore, when you have 2 molecules with a bond or something oscillating, there's a potential that has a minimum at the equilibrium position, and the oscillations are governed by some harmonic oscillator. When you have photons in space-time traveling, there is a set of harmonic oscillators that correspond to photons. Many applications, endless amount of applications for the harmonic oscillator. So we really want to understand this system quantum mechanically. And what does that mean? Is that we really want to calculate and solve the Schrödinger equation. This is our first step in understanding this system. There's going to be a lot of work to be done even once we have the solutions of the Schrödinger equation. But the first thing is to figure out what are the energy eigenstates or the solutions of the Schrödinger equation for this problem. So notice that here in this problem, there's an energy quantity. Remember, when you have a Hamiltonian like that and people say, so what is the ground state energy? Well, I have to find the ground state wave function, I have to do things, give me an hour, I'll find it and all that. But if you want an approximate value, dimensional analysis will do it. Roughly, what is it going to be? Well, with these constants, how do you produce an energy? Well, you remember what Einstein did. You know that h bar omega has units of energy. So that's an energy associated with Lagrangian, energy-like quantity. And we expect that that energy is going to be the relevant energy. And in fact, we'll find that the ground state energy is just one half of that. There's another quantity that may be interesting. How about the length? How do you construct the length from these quantities? Well,
All right. How do we get a length of this?
you can start
see.
doing
I don't know.
m omega h bar and put powers and struggle. I hate doing that. I always try to find some way of doing it and avoiding that thing. So I know that energies go like h over h squared over m length squared. So I'm going to call the length a quantity a. So ma squared, that has units of energy. And you should remember that because energy is p squared over 2m, and p by de Broglie is h bar over some lambda. So h bar squared, lambda squared, and m here, that's units of energy. So that's a length. On the other hand, we have another way to construct an energy is with this thing, m omega squared length squared. So that's also m omega squared a squared. That's another energy. So from this equation, I find that a over 4, a to the fourth, is h squared over m squared omega squared. And it's a little complicated. So a squared is h bar over m omega. So that's a length. Length squared. I don't want to take the square root. We can leave it for a moment there. But that's important because that's a length scale. And if somebody would ask you, in the ground state, how far is this particle oscillating? You'll say, probably about a square root of this would be the natural answer, and probably about right. So, okay, energy and units is very important to begin your analysis. So, what is the Schrödinger equation? The Schrödinger equation for this thing is going to be, of course, minus h squared over 2m d second psi dx squared plus the potential 1/2 m omega squared x squared psi is equal e psi. And the big problem is that I don't know psi and I don't know e. Now, there's so many elegant ways of solving the harmonic oscillator. You will see those next lecture. Alan Adams will be back here, but we all have to go through once in your life through the direct, uninspired method of solving it. Because most of the time when you'll have a new problem, you will not come up with a beautiful, elegant method to avoid solving a differential equation. You will have to struggle with the differential equation. So today we struggle with the differential equation. We're going to just do it. And I'm going to do it slow enough and in detail enough that I hope you follow everything. I'll just skip a couple of things, but there will be one-line computations that I will skip. So this equation is some sort of fairly difficult thing, and it's complicated and made...
So let's write it down. Let's get started here. We're 2m dx squared plus 1/2 m omega squared x squared. Yeah. E omega.
Fairly unpleasant by the presence of all these constants. What kind of equation is that with all these constants? It shouldn't be there, all these constants, in fact. So this is the first step, cleaning up the equation. We have to clean it up. Why? Because, you know, the nice functions in life, like y double prime is equal to minus y, have no units. The derivatives create no units. Y has the same units of that, and the solution is sine of x, where x must have no units because you cannot find the sine of 1 centimeter. So this thing, we should have the same thing here. No units anywhere. So how can we do that? This is an absolutely necessary first step. If you're going to be carrying all these constants, you'll get nowhere. So we have to clean it up. So what I'm going to try to see is that, look, here is psi, psi, and psi. So suppose I do the following thing, that I will clean up the right-hand side by dividing by something with units of energy. So I'm going to do it the following way. I'm going to divide all by 1 over h bar omega, and this 2, and I'm going to multiply by 2. So multiply, I'm sorry, not divide all by this. Multiply by 2 over h bar omega. So what do I achieve with that first step? I achieve that these 2's disappear. Well, that's not too bad, not that great either, I think. But in the right-hand side, this has units of energy. The right-hand side will not have units of energy. So what do we get here? So we get minus, the h becomes an h alone, over the m disappears, so m omega, the second psi, dx squared, the 1/2 disappears, so m omega over h bar, x squared psi, equals 2e over h bar omega psi. Now it looks actually quite better already. Should agree with that. This looks a lot nicer. Now I can use a name for this. I want to call this the dimensionless value of the energy. So a calligraphic E. It has no units. It's telling me if I find some energy, that energy really is this number, this pure number is how many times bigger is E with respect to h omega over 2. So I'll write this now as E psi. And look what I have. I have no units here. And I have a psi, and I have a psi, but things have worked out already. Look, the same factor here, h over m omega, is upside down here. And this factor has units of length squared. Length squared, that's dd length squared, has no units. And here is 1 over length squared. 1 over length squared times length squared. So things have worked out. And we can now simply say x is going to be equal to a new variable. This is going to be your new variable for your differential equation, in which a is this thing. And then this differential equation, probably I'll go here, really has cleaned up perfectly well. Oops. So how does it look now? Well, it's all done actually, because if you have x equal au, d dx by chain rule is 1 over a ddu. And two derivatives with respect to x is 1 over a squared, d second du squared. And this thing is a squared, so actually you cancel this factor, and when I write x equals to au, you get an a squared times this, and a squared times this is 1. So your differential equation has become minus d second psi du squared, where u is a dimensionless quantity, because this has units of length, this has units of length, no units here. No units. So minus d second du squared plus u squared psi is equal to e psi.
This is the kind of thing I need to practice, because this is the kind of thing I wouldn't have figured out on my own.
Without being distracted by this endless amount of little trivialities. So, but still, we haven't solved it, and How are we going to solve this equation? So let's again think of what should happen. Somehow it should happen that these e's get fixed. And there's some solutions just for some values of e's. It's not obvious at this stage how that is going to happen. Yes. Here, for example, let me do this. This term. H bar over m omega is minus, from that equation, a squared. But dx squared is 1 over a squared ddu squared. So the a squared cancels. And here the x is equal to a squared times u, so again cancels. Okay, so what is the problem here? The problem is that most likely what's going to go wrong is that this solution for arbitrary values of e is going to diverge at infinity, and you're never going to be able to normalize it. So let's try to understand how the solution looks as we go to infinity. So this is the first thing you should do with an equation like that. How does the solution look as u goes to infinity? Now, we may not be able to solve it exactly in that case either, but we're going to gain insight into what's happening. So here it is. When u goes to infinity, this term, whatever psi is, this term is much bigger than that, because we're presumably working with some fixed energy that we still don't know what it is, but it's a fixed number, and for u sufficiently large, this is going to dominate. So the equation that we're trying to solve as u goes to infinity, the equation sort of becomes psi double prime, prime is for two derivatives, is equal to u squared psi. Okay, so how do we get an idea of what solves this? It's not all that obvious. It's certainly not a power of u, because when you differentiate a power of u, you lower the degree rather than increase the degree. So what function increases degree as you differentiate? It's not a trivial function. Cannot be a polynomial. If it would be even a polynomial, if you take two derivatives, it cannot be equal to x squared times a polynomial. It's sort of upside down. So if you think about it for a little while, you don't have an exact solution, but you would imagine that something like this would do it, an e to the u squared. Because an e to the u squared, when you differentiate with respect to u, you produce a u down. You take one derivative. When you take another derivative, well, it's more complicated. By one term, you will produce another u down. So that probably is quite good. So let's try that. Let's try to see if we have something like that. So I will try something. So I'll try psi equals to, I'm going to try the following thing. E to the alpha u squared over 2, where alpha is a number. I don't know how much it is. Alpha is a number. Now, I could try this alone, but I actually want to emphasize to you that if this is the behavior near infinity, it won't make any difference if you put here, for example, something like u to the power k. It will also be roughly a solution. So let's see that. So for that, I have to differentiate. And let's see what we get. So we're trying to see how the function behaves far, far away. You might say, look, probably that alpha should be negative, but let's see what the equation tells us before we put anything in there. So if I do psi prime, you will get what? You will get one term that will be alpha u times this u to the k e to the alpha u squared over 2, where I differentiated the exponential. And then you will get a term where you differentiate the power. So you get k, u to the k minus 1, e to the alpha u squared over 2. If you take a second derivative, well, I can differentiate the exponential again, so I will get alpha u now squared, because each derivative of this exponent produces a factor of alpha u to the k, e to the alpha u squared over 2. And a couple more terms that they all have less powers of u, because this term has u to the k plus, already has u to the k plus 1, and this has u to the k minus 1. They differ by 2 powers of u. So for illustration, please, if you want, do it. 3 lines. You should skip 3 lines in your notebook if you're taking notes, and get the following. No point in me doing this algebra here. Alpha u squared over 2, because actually, it's not all that important. Over alpha 1 over u squared plus k k minus 1 over alpha squared, 1 over u to the fourth. That's all you get. But this is, look, this is alpha squared u squared times psi times these things. 1 plus 2k plus 1 over alpha 1 over u squared. So when u goes to infinity, your solution works because these things are negligible, so you get a number times u squared. That is the equation you're trying to solve up there. And therefore, you get that equation if alpha squared is equal to 1. And that means really that alpha can be plus minus 1. And roughly, this solution near infinity, probably, there's two solutions. This is a second order differential equation, so even near infinity, there should be two solutions. So we expect that as u goes to infinity, psi of u will be some constant a times u to the k times e to the minus u squared over 2, that's for alpha equal minus 1, plus b u to the k e to the plus u squared over 2. And what is k? Well, we don't know what is k. It seems to work for all k. That may seem a little confusing now, but don't worry. We'll see other things happening here very soon. So look at what has happened. We've identified that most likely your wave function is going to look like this at infinity. So we're going to want this part not to be present. So presumably we're going to want a solution that just has this, because this is normalizable. The integral of any power times a Gaussian is convergent. So this can be normalized. The Gaussian falls so fast that any power can be integrated against a Gaussian. Any power, however big, doesn't grow big enough to compensate the Gaussian. It's impossible to compensate the Gaussian. So we hope for this. But we want to translate what we've learned into practical advantage in solving the differential equation, because after all, we wanted insight how it looks far away, but we want to solve the differential equation. So how can we use this insight we now have to simplify the solution of the differential equation? The idea is to change variables a little bit. So write psi of u to be equal to h of u, that's times e to the minus u squared over 2. Now you can say, why, what are you doing? Are you making an approximation now that this is what is going to look far away? Or what are you putting there? And I'm not making any approximation. I'm just saying, whatever psi is, it can always be written in this way. Why? Because if you have a psi of u, you can write it as psi of u over e to the minus u squared over 2 times e to the minus u squared over 2. Very trivially, this can always be done as long as we say that h is arbitrary. There's nothing, no constraint here. I have not assumed anything, nothing. I'm just hoping that I have a differential equation for psi, that because this is a very clever factor, the differential equation for h will be simpler. Because part of the dependence it has been taken over. So maybe H, for example, could be now a polynomial solution because this part has been taken care of. So the hope is that by writing this equation it will become an equation for H of U, and that equation will be simpler. So will it be simpler? Well, here again, this is not difficult. You're supposed to plug into equation 1. This is equation 1. Plug into 1. To 1. I won't do it. It's 3 lines of algebra to plug into 1 and calculate the equation for H of U. You should do it. It's the kind of thing that one should do at least once. And so please do it. It's 3-4 lines. It's not long. But I'll just write the answer. So by the time you substitute, of course, the e to the minus u squared over 2 is going to cancel from everywhere. It's very easy here. You just need to take 2 derivatives, so it becomes a second-order differential equation. And indeed, it becomes a tractable differential equation. The second h, the u squared, minus 2u, the h du, plus e minus 1, h equals 0. Okay, that is our equation now. So now we face the problem of finally solving this equation. So before we start, maybe there are some questions of what we've done so far. Let's see, any questions? Yes.
How there'll be equations linear, so can we just like say we have e to the minus u squared over 2, and you stuck in that u to the k.
I'm sorry, it's here, this thing?
Yeah. You didn't just power series what's going on at 0 with those u to k terms and some of a bunch of them.
No. This is the behavior as u goes to infinity. So I actually don't know that the function near 0 is going to behave like u to the k. We really don't know. Yeah, it suggests to you that maybe the solution is going to be near 0 u to the k times some polynomial or something like that, but it's not that, because this analysis was just done at infinity. So we really have no information still what's going on near 0. Other questions? Yes.
So is here some arbitrary
At this moment, actually, it doesn't matter, is it right? So, doesn't matter. The analysis that we did here suggested could be anything. That's why I just didn't put it into h of u. I didn't put it because it would be strange to put here a u to the k. I wouldn't know what to make of it. So at this moment, the best thing to say is we don't know what it is, and maybe we'll understand it, and we will. In a few seconds, we'll sort of see what's going on. Okay, so how does one solve this equation? Well, it's not a trivial equation again, but it can be solved by polynomials, and we'll see that. But the way we solve this equation is by a power series expansion. Now, you could do it by hand first, and I did it when I was preparing the lecture yesterday. I said, I'm going to just write h equals h of u equal a constant a0 plus a1u plus a2u squared plus a3u cubed. And I plugged it in here. And I just did the first few terms and tried to see what happened. And I found, after a little thinking, that A2 is determined by A0, and the A3 is determined by A1. Once you substitute, it's not obvious when you look at this, but that happens. So, when you face a problem like that, don't go high power to begin with. Just try a simple series and see what happens, and you see a little pattern, and then you can do a more sophisticated analysis. So what would be the more sophisticated analysis? To write h of u equal the sum from j equals 0 to infinity, aj u to the j. Then, if you take a derivative, because we're going to need the derivative, dh du would be the sum from j equals 0 to infinity, j times aj u to the j minus 1. You will say, that doesn't look very good because for j equals 0, you have 1 over u. That's crazy. But indeed, for j equals 0, the j here multiplies it and makes it 0. So this is okay. Now, the term that we actually need is minus 2u dh du. So here, minus 2u dh du would be equal to the sum from j equals 0 to infinity, and we'll have minus 2 j aj u to the j. The u makes this j minus 1j, and the constant went there. So here is so far h. Here is this other term that we're going to need for the differential equation. And then there's the last term that we're going to need for the differential equation. So I'm going to go here. So what do we get for this last term? We'll have to take a second derivative. H prime was there, so this second h du squared will be the sum from j equals 0 of j times j minus 1 aj u to the j minus 2. Now, you have to rewrite this in order to make it tractable. You want everything to have like u to the j's. You don't want actually to have u to the j minus 2. So the first thing that you notice is that this sum actually begins with 2. Because for 0 and 1 it vanishes. So I can write j times j minus 1 aj u to the j minus 2. Like that. And then I can say, let j be equal to j prime plus 2. And if j is, look, j begins with 2 in this sum. So if j is j prime plus 2, j prime will begin with 0. So we've shifted the sum. So it's j prime equals 0 to infinity. And whenever I have a j, I must put j prime plus 2. So j prime plus 2, j prime plus 1, a j prime plus 2, u to the j prime. Wherever I have j, I put j prime plus 2. And finally, you say j or j prime is the same name, so let's call it j. J equals 0. J plus 2, j plus 1, a j plus 2, uj. Okay.
Ooh.
So we got the series wherever I had j, I put j prime plus 2. And finally, you say j or j prime is the same name, so let's call it j. J equals 0. J plus 2, j plus 1, a j plus 2, uj. Okay. So we got the series expansion of everything, so we just plug into the differential equation. So where is the differential equation? It's here. So I'll plug it in. Let's see what we.
So let's just rewrite the differential equation here. D squared dh du squared minus 2u dh over du plus minus 1h equals 0.
get. We'll get sum from j equals 0 to infinity. Let's see, the second derivative is here. J times j plus 2 times j plus 1 times j plus 1, aj plus
J plus 2, j plus 1.
2, uj, so I'll put it here, uj. Good, that's the second derivative term. Now this one, it's easy, minus 2j aj, and the uj is there, so minus 2j aj. Last term is just e minus 1, because it's the function this times aj as well. That's h. And look, this whole thing must be 0. So what you learn is that this coefficient must be 0 for every value of j. Now it's possible to, here is aj and aj, so it's actually one single thing. Let me write it here. J plus 2 times j plus 1, aj plus 2 minus 2j plus 1 minus e aj uj. I think I got it right. Yes. And this is the same sum. And now, okay, it's a lot of work, but we're getting there. This must be 0. So actually that solves for aj plus 2 in terms of aj. What I had told you that you can notice in 2 minutes if you try it a little, that a2 seems to be determined by a0 and a3 seems to be determined by a2. So this is saying that aj plus 2 is given by 2j plus 1 minus e over j plus 2, j plus 1, aj. A very nice recursion relation. So indeed, if you put the value of a0, it will determine for you a2, a4, a6, a8, all the even ones. If you put a value for a1, it will determine for you a3, a5. So a solution is determined by you telling me how much is a0 and telling me how much is a1. Two constants, two numbers. That's what you expect from a second order differential equation. The value of the function at a point, the derivative at a point. In fact, you're looking at a0 and a1 as the two constants that will determine a solution. And this is the value of h at 0. This is the derivative of h at 0. So we can now write the following facts about the solution that we have found. So what do we know? That solutions fixed by giving a0 and a1 that correspond to the value of the function at 0 and the derivative of the function at 0. And this gives one solution. Once you fix a0, you get a2, a4, and this is an even solution because it has only even powers. And then from a1, you fix A3, A5, all the odd ones is an odd solution. Okay. Well, we solved the differential equation, which is really, in a sense, bad, because we were expecting that we can only solve it for some values of the energy. Moreover, well, you have A0, you get A2, A4, A6, A8. This will go on forever and not terminate, and then it will be an infinite polynomial that grows up and doesn't ever decline, which is sort of contradictory with the idea that we had before, that near infinity, the function was going to be some power, some fixed power times this exponential. So this is what we're looking for, this h function now. And it doesn't look like a fixed power, it looks like it goes forever. So let's see what happens eventually when the coefficients, the value of the J index is large. For large J, AJ plus 2 is roughly equal to, for large A, whatever the energy is, sufficiently large. The most important here is the 2J here, the J and the J, so you get 2 over J AJ. So roughly for large J, it behaves like that. And now you have to ask yourself the question, if you have a power series expansion whose coefficients behave like that, how badly is it at infinity? How bad is it? You know, it's a power series expansion because your H was all these coefficients, and suppose they behave like that, they grow in that way, or decay in this way because they're decaying. Is this a solution that's going to blow up, or is it not going to blow up? And here comes an important thing. This is pretty bad behavior, actually. It's pretty awful behavior. So let's see that. That's pretty bad. So, how do we see that? Well, you could do it in different ways, depending whether you want to derive that this is a bad behavior or guess it. I'm going to guess something. So I'm going to look at how does e to the u squared behaves as a power series. Well, you know, as a power series, the exponential is 1 over n u squared to the n. Here's n factorial, n equals 0.
I'm actually going to just pause it right now because we've hit about the end of the day. I've got some plans later, so I'm not going to be able to keep doing this one. I was hoping to get through the whole lecture, but I had to slow it down, so I couldn't finish it. So this is crazy complicated. I don't know if you guys felt that way when you're going through this, but there's tons of steps. There's a lot of, well, let's try this and let's look at some of this behavior and let's do this. So part of me is wondering whether it's not going to be worthwhile to kind of comb over this and understand every step that was done in this solving of a differential equation. I know at a high level that solving a differential equation is basically there's no real given analytic procedure. You're just kind of like, all right, let's try this as a solution and then see what it pops out. So if we look just at the super high level, which I may not go further than this, but if we just look at the super high level, what are we starting with? Well, we have this differential equation that has a bunch of h bars and m's and this kind of thing. So we're cleaning it up, substituting out different terms so that it'll be a little cleaner. And then we get this fairly clean differential equation. And then we're trying to figure out, okay, what is happening as this new differential equation? What happens as it goes to infinity? What kind of behavior is it that we're looking at? we are trying to solve this. So we're noticing that this at the infinity, at the far out, we have basically the second derivative of psi is roughly equal to this u squared psi. Now, what kind of equation would lead this? Well, he suggests that, well, maybe, e to the power of u squared is not a bad starting point. So we kind of try this out. We plug it into some places here. We get some, behavior here. Then there's, well, a lot more stuff here. So there's a lot of stuff that I'm not even 100% following right now, but we are now plugging in a bunch of these second derivatives, trying to figure out what this psi of u would be. We want to kind of get a little bit of a better idea of it. So now we're doing this power series to try to figure out what this h of u is, this sort of generalized idea of what the coefficients are going to be. And right now we've gotten to a point where we've plugged everything in and we realize that we've got some kind of behavior that maybe we don't exactly want for this. So this is still a little bit, as you can tell by my kind of hasty summary of it, there's still a lot of stuff that I'm not completely understanding about this. Now there's going to be a kind of question of whether it makes sense to fully understand this derivation. Now the way this derivation was presented is that generally speaking, we're not going to have to go through this. So I doubt that on the exam, I'm going to go through the brute force sort of differential equation approach that he's going through here. And the way that he's treating it makes me think that this is more to kind of give a kind of hasty overview of how we're getting the solutions of these equations so that they seem mathematically plausible or mathematically rigorous, rather than, we're going to be expected to go through this process again and again. So I have to kind of make a decision. I may not go through this. I'm probably not going to go through a full description of this differential equation and how it works immediately, unless it shows up in the problem sets. But I think at the same time, I don't like that I don't understand this. This is definitely something that I'm putting in kind of a little asterisk right now. And so I'm going to go touch base on this tomorrow. I'm going to start right where we left off at an hour and 10 mark in this lecture. And I'm going to hopefully finish up lectures 9 and 10. I may just put a bookmark in this point right now. Aside from the fact that I know generally what we're doing is we're trying to find the family of solutions that fit this differential equation. And we've gone through a bunch of work to get there. Now, exactly what the work was and what motivated every single step, I mean, there's a lot of stuff happening here. And you can see that I was watching at 1x speed and he's going through it all pretty quickly, jumping over some steps, saying, well, and then this, not really explaining how you would come to those logical conclusions at every single point in time. So I don't want to give Professor Zubak, a bad deal. I just think that this is just sort of my problem as well, because haven't done differential equations for about 8 years, haven't solved any recently. And so for a lot of it, it's a little bit rusty for me, whereas presumably for MIT students, they have not done it nearly a decade ago. So what I'm going to do is I'm just going to put a pause in this right now, not going to touch anything, and I'm going to jump back in on this tomorrow, start in on this lecture. As I said, this bothers me that I don't understand this fully, but it may not be as relevant to the problem solving. It may be the case that once we solve this differential equation, I don't need to go through the work of proving it, just the way how there are numerous propositions that have been discussed in the course that I haven't myself proved. Now we'll go through the problem set. If it looks like the differential equation approach, getting a familiar grasp on this is going to be important. I might do a full Feynman technique, but given how long the presentation was, my sense is that's probably going to be about an hour to do that. So I have to kind of just decide whether that's going to be worthwhile, but I think I'm going to have a better picture of that when I zoom out, see how much time I have. So with that note, thank you everyone who's been following, who's maybe listening right now, who's been following me today. I'm going to be back tomorrow working on it again. This has been day 2. And overall, I feel pretty good. I think, aside from this last class, when they had the clicker questions, I got most of them right. And the ones that I got wrong, I felt like were pretty minor mistakes, not really fundamental. I have no idea what's going on kind of problems. And so I think that when we get to the problem set, I'm going to feel fairly good. There might be some having to learning some other things, but I mean, that's just sort of how it goes. Yeah, so I feel pretty good about this. This differential equation process is hard, but solving differential equations is always hard, and it requires a lot of mathematical tricks and trying stuff. And so you can see that he's really like throwing a lot at the problem. So I'm going to end the stream now, but I will be back online tomorrow at 8 a.m. All right.